Welcome to the third edition of the Lifelong Learning and Personalization in Long-Term Human-Robot Interaction workshop, where we take a leap from the traditional approaches of HRI towards the person robots of the future. I'm Bahar Irfan. I'm a postdoctoral researcher and a Digital Futures Fellow at KTH Institute of Technology here in Stockholm. So welcome to the beautiful weather. And my research focuses on creating person robots that can continue to learn and adapt to assist everyone in their daily lives. And I have an excellent organization committee. First of all, we have Aditi Ramachandran. She's the Chief Robot Officer at Robotics, where she works on building education robots and oversees all software development at the company. Then we have Mariacarla Staffa. She's an assistant professor in human-robot interaction, artificial intelligence, and cognitive robotics at the University of Naples, Partapone in Italy. And she's mainly interested in exploring computational neuroscience and cognitive robotics to generate innovative strategies and solutions for scientific problems and technological limitations. And finally, we have Hatice Gunes. She's over here. She's a professor of effective intelligence and robotics, AFAR, and the director of the AFAR lab at the University of Cambridge in UK. Her expertise is in the areas of predictive computing and social signal processing, cross-fertilizing research and multimodal interaction, computer vision, machine learning, and social robotics. So we previously organized this. As I said, this is the third edition of the workshop, but it goes way back to 2019, where I first founded with Aditi and other co-organizers the Personalization in Long-Term Robot Interaction workshop. And from then, Hatice and other co-organizers made the Lifelong Learning for Long-Term Robot Interaction workshop at Roman, and then we combined, and there we go, we had LEAP-HRI workshop. And also Mariacarla organizes the Bevill workshop, Behavior Adaptation for Interaction Learning and Assistive Robotics. And I think there's gonna be a new edition coming up for Roman, so stay tuned for that one. And we also have a special issue with other co-organizers in Fourth Frontiers that's already finished. I mean, but check the papers out. And if you wanted to watch the previous workshops, they're all online on the websites for the recordings, and we're also recording this workshop. They will be available after the workshop on the website. So quickly, I'm going to go through the program, and then I'll lead to Hatice. So we are the first speaker is going to be Pablo Barros from Sony R&D. And then we're gonna go with the 3 paper talks, 2 of them here and 1 of them online. And then we're gonna take a breakout session, discuss a very hot topic in AI. From there, we're gonna refresh with a good coffee break. Before the coffee break, we have Dorsa from Stanford University. Our second keynote is gonna talk about aligning robots with preferences. Then the coffee break, and finally our 2 more talks, 1 of them online, 1 of them here, and finally the debate of the year. Definitely come to all of them. They're all amazing. I'm super happy with this program. I would suggest scanning this really quickly, but you will still have time before the debate as well. So we're going to use it during the debate and the discussions. We're going to talk about the workshop organization and the workshop structure and your feedback. And finally, for our online participants, welcome as well. I guess you can see me. There we go, I'm here. And except for the organizers and the speakers, I would kindly ask you to mute yourselves and turn off your cameras so that there's no disturbances. But other than that, and if you can write through the chats, we have 2 online, Aditi and Mariacarla, that they will be moderating that part, and we'll be moderating with Hatice the in-person questions. So, with further ado, I leave the stage to Hatice.
Hello everyone, I'm Hatice Gunes from University of Cambridge, and I'm chairing this session where we have the speaker being Dr. Pablo Barros. So he's a machine learning scientist at the moment at Sony Research and Development Center in Brussels. And before that, he obtained his PhD from the University of Hamburg in computer science. And he worked on various topics, including effective computing and social robotics, more specifically facial expression recognition, but also social agents and how we can actually develop more or better perception models for those. He actually, I think he didn't provide it as part of his CV, but he even has best paper awards on some of the topics that he'll be talking about today. So the title of his talk is How Can We Overcome Feature-Based and Contextual Biases When Learning Facial Expression Representations? Pablo, thank you again for accepting, and the floor is yours.
Oh, thank you very, very much. Can you hear me well?
Yes.
Yes, I see heads shaking. Perfect.
Yeah.
Okay, perfect. Thank you. Thank you so much, Hatice. Thank you so much, Bahar, for the invitation. It's quite nice. I'm sorry I'm not there in Stockholm. I had some vacations that was scheduled for a long, long time, and I went halfway through the word. So sorry for that, but yeah, I'm very happy to be here. So yes, as Hatice mentioned, I will talk about first of all understanding and how can we counter these biases, which are extremely important when representing face expressions on different scenarios, right? I worked with face expressions for a while, and we always encounter these problems, how to, these models that we develop on face expression recognition, how to make them actually usable on different scenarios, on different applications, right? And we realized that there are two types of problems that usually are addressed with face expression recognition: a generalization problem and a personalization problem, where on a generalization, you try to use these models in a more general case possible. You train these models with a lot of information, a lot of face expressions in this case, and try to recognize information that are universally spread around this person. And this is very cool for some applications and very necessary for some applications. But for some other applications, personalization is the case. You have to understand how a specific person expresses emotions and changes his emotion expressions over time. But in all of these cases, and majority of the applications of face expression recognition, we have to understand that this is usually not the case, that face expression recognition is not an end task. If you treat it as an end task, you will have a lot of problems, because it's not a tool, right? And this is, I see a lot of people using these ready models, these shelf models, these models which are already ready and trained and doing classification as an end task. As I take this module, I apply to my solution, and from there on, I have a result. But face expression recognition is much more than that, right? Because every person expresses emotions differently, depending on the scenario, depending on the context. And if you try to approach this in a very generalized way, probably your scenario will be lacking a lot of information, and the role of the face expression recognition in your scenario will be very, very much impacted, right? However, there's a lot of applications with face expression recognition nowadays, from car development to human analysis, to robotics, to human-robot interaction, all of that. And people usually don't think about this responsibility of providing these systems to this plethora of applications, which are completely different in nature from each other. And usually don't have an understanding of the impact that these models have on these applications. And working together with Alessandra Sciuti from IIT, we try to understand, what are the biases on these models, and how can we understand these biases, and how to understand the impact that these biases have on these specific scenarios, but also how to fix it, how to counter it in a very efficient manner, because we cannot be retraining these models over and over again with different data, right? So this talk, I will talk a little bit about our findings on this area and our suggestion and our future work on this field. So the main thing of this talk, but also on face expression recognition itself over the last 10 years, is deep learning, right? Deep learned face expression recognitions became the default option. You learn face expressions using convolutional neural nets, now with transformer neural nets. And these networks, they learn implicit features from the face, which are then fine-tuned based on a certain scenario, on the affective concepts of a certain scenario, right? Usually, this is based on images or a sequence of images, but what these networks do is they learn specific parts of these images that are shared among different persons that represent a certain affective concept, right? And usually these networks go for a concept of extreme generalization. You have an affective concept, let's say a categorical emotion label like happy or sad, and you have thousands of images of someone labeled as sad, thousands of images someone labels as happy. And this network learn how to generalize and how to find these characteristics of the face that are matched to these specific concepts, right? Usually in the wild scenario. So you have really thousands of persons all over the world crowded from the internet. And these networks are very efficient on that. They learn very well, they represent expressions very well, but they are very expensive to adapt. If I have a specific scenario, for example, a driving scenario, I want to detect face expression of someone which is driving. It's a very, very specific range of emotions this person displaying, and a very specific range of applications this can be used. And to adapt these very general networks to this scenario, you really need to retrain the whole network, evaluate the whole network again, and this is complicated. If you transfer this to the human-robot interaction, for example, where you have even more scarce resources, whether for training or whether for getting images, this becomes a very, very large problem. And that's something we try to tackle. So these facial expression representations I mentioned usually based on convolutional face, convolutional operations that learn these patterns on the face. These patterns became very efficient, and depending on the face, the network do not look the whole face, but look to specific structures on the face, mouth position, eyes positions, cheek positions. And there are some quite interesting work that also relate to this, for example, with the facial action units, which are human-based analysis on faces. And these networks are trained completely implicit without human feedback at all, which is quite interesting, right? And allow us to have really this reconstruction of the face representation in a very dense representation, which is great for us. And this is the whole basis of how these faces are learned. However, when you go to the affective representation, things change. Then you're not only looking for the structures of the face you are learning, but how these structures combine, and together they represent a certain affective concept, whether happiness, sadness, or even a continuous representation, if you're talking about arousal valence or pleasure in arousal or any other representation you have, right? But while when representing the face, you have different problems like illumination, like quality of the camera, like facial structures that are not present in a certain scenario. When you're presenting the affective information that these faces carry, the problems are way more complex and way more difficult to handle because emotions and emotion interpretations are subjective to the scenario, to the person who is expressing, to the person who is recognizing or who is labeling this. And that comes back to a very interesting concept, which is the universal emotions, right? You have this specific set of emotions that happens all over the world, which is great on a paper and works nicely for some psychological experiments. But if you apply this to computational models, this becomes dangerous, because that means that these models are learned to detect happiness in a certain way for all over the world in all the applications you have. And that's complicated because in specific scenarios, happiness is shown in a different way than other scenarios by different persons, maybe the same person, but a different time of the day. And usually when you train these generalized models based on universal emotions, this is not accounted for. They are extremely sensitive to changes on the expressions, and then they end up classifying these emotions differently or wrongly even, which then if you're treating these models as a shelf application, you're not caring about how they work, your application will then be wrong because you will not understand that the representation of the emotions of the model are somehow skewed based on your scenario, right? And that goes to the labeling, because most of these models are trained in a supervised manner. So someone has to collect the data and label these data according to a certain set of emotions. But this labeling is extremely biased to whoever is labeling these emotions, whoever is labeling these faces. If the person thinks that this is happy or sad, or because of this specific scenario this network was trained, this is happy or sad, this is extremely embedded into the network knowledge. And to change this, to adapt this, it's very difficult, it's a huge effort for doing that. So understanding also how these models were trained and how these models were constructed before you apply these models in your scenario is extremely important, because then you can find out already some biases that might be affecting your application. We started these categories, first the facial representation biases, and then the contextual representation biases, so the affective representation biases. And we started with some work on how faces are represented in the convolutional neural networks. And what is the impact of, for example, because these are all images, right? So this is extremely sensitive to typical problems from computer vision, like noise, like illumination of the image, distance of the image, motion, all of that. And this alone, only by changing these characteristics on the image, we found out that there is a high impact on the classification of these images to the network, which is of course expected. But when you take these models as granted, you don't really think about it because you think it's a module that I apply to my solution, right? So if my camera is, for example, there is a little bit of motion in the camera, we found out that for different persons, every bar on this image refers to images or not accuracy, but performance of the network of images of different persons when there is different characteristics on these images. If you have motion or very simple noise like Gaussian noise or pepper noise in the image, the performance of the network is already decreased so much that the network become unreliable. The information this network is classifying is already unreliable compared to the original image, the image without any noise or without the changes on illumination or so. And that alone, this is a common problem, of course, for computer vision, and that's addressed, and there is a lot of solutions for that. But all of the solutions demand adapting the network, demand understanding what the network is actually doing. And if you use this network as a package and just try to trust it, this will not work well, right? And this has a massive impact on the scenario you're talking. If you have a driving scenario, the illumination is completely different than if you have a scenario where you're evaluating persons in an office, for example, which has a standard illumination, a same camera, and all of that. And this can be represented. I mean, there are so many data sets for emotional expression recognition over the internet, all of them with different characteristics and different style, different person, different affective representations. However, if you train the same network and you apply this network to all these data sets, you can see that when these networks are trained with specific data sets, they do learn very unique representations of faces, right? They pay attention to different structures depending on the characteristics of these data sets. So again, if you want to use one of these models on your solution, try to understand how and which data this model was trained on, because it can change drastically what's the input and output and how this output will be represented, right? So try to understand the problem and how these models are working. Really help a lot on choosing which models to use for your own solution. After understanding that there is all these biases, and these biases actually affect or impact the information that these networks output, we try to study, okay, how can we adapt this in an efficient manner, right? You have different applications of it, different word representations represented by different data sets, crawled from the internet with actors, black and white, from adults, from children, from elderly persons. All of them have their own characteristics, right? And we separated this adaptation into two steps. First of all, the adaptation of the representation learning itself, how these structures are detected on the data, and how can we adapt this in a fast manner. But also the adaptation of the affective representation itself. What is the emotional concept we can take from them, and how can we adapt this in a timely manner and efficient way, right? The first one we proposed recently, what we call CHOW, which is a plugin layer that you attach to the last layer of a neural networks, and we evaluated this with two different types of encoders, of facial encoders. One supervised, the face channel, and the prior knowledge, which is a generative adversarial network that is trained on an unsupervised or self-supervised manner, if you want to call it like that. And we wanted to see is how can this plugin change the representation of these encoders without retraining the whole encoder to deal with the needed representation of specific data sets. How can we adapt it in a very fast way? So this plugin is composed of inhibitory layer, a inhibitory convolution layer that is trained using a contrastive loss in a supervised manner to try to change the representation of the last convolutional layer of these encoders. And just that. So we're not changing the encoder structure at all. We're just creating a mask that will deform this last representation to a specific data set. And this is very fast to train and very, very easily to adapt to specific data sets without a lot of images. And that was quite interesting for us. So what we show is when we train this model in different data sets, and we evaluated on 4 different data sets on the 2 different encoders, we see that when the Chow adaptive layer is applied, the performance of these networks on this data set increase, in some cases very drastically, because this deformation of the last layer implies on I'm changing how these networks are representing faces. So the parts of the faces that are important for that specific data set are changed, but not on the entire encoder, only on how they are passed to a decision-making layer in a very, very fast manner. And what we noticed as well is that this encoded representation, for example, in this case, on the top, on the bottom right image, you have the latent representation of the JAF dataset, which is a very small dataset that has only, is labeled as categorical emotions and have only 20 images per emotion. And so it's a very, very small dataset. And if you have this encoded representation, for example, on the prior knowledge network, the performance is very poor. And the original network trained on thousands of the images of the internet, the representation of these emotions, each of emotion category represented by a color, it is difficult for the network to distinguish them. As soon as we deform this representation with the Chow adaptive layer, we can see that the clusters are easily identifiable. And as soon as the cluster is easily identifiable, the network is able to identify way faster in a way faster way to detect the right emotion, categorical labels in this case. And with that, the performance of these networks are increased quite a lot, specifically for the prior knowledge layer, for the prior knowledge encoder, in a very efficient manner, because you are training only a few meters per time instead of the whole encoder. And you can do this. We are also investigating this now with Alessandra, how to do this on a robot, using the iCab robot, for example. And this will be quite nice because you have way less images, for example, to adapt the network instead of retraining the whole model. The second step was to, how can we, once we have these strong representations, how can we then categorize them in different effective concepts in a fast, also efficient manner without having to retrain the whole network? We started in Hamburg, we started investigating and experimenting using clustering, specifically self-organized networks that are very, very simple networks to train, that get a certain facial encoding and try to cluster this facial encoding into similar concepts. And we can see that with a very low number of training iterations, 100 training cycles, we can already reconstruct specific clusters of facial representations from different persons. And these clusters are very robust. And after a while, they become a very general emotional representation, which is quite nice because they're clusters, I can also recluster them and take only parts of them to a specific scenario without having to retrain everything, without having to have a new training cycle. And this was quite effective. Because I can recluster them, I can also create individualized emotional concepts within these big clusters, this large cluster. And that was, we did a quite interesting work also in Hamburg that showed that this is also unsupervised. So there is no label, there is no bias coming from the labels. This is all based on the face expression encoding itself. And we found out that, of course, different persons express emotions differently, but how these emotions are connected to each other and how they are closer or far from each other changes also from person to person. And just by reclustering this general cluster, we can find out relations between different emotions that changes from the person DC and the person JE here, for example, which is quite interesting. And because these networks are always clustering these emotions, that means that they can keep on a lifelong clustering while the person is perceived by this robot in this scenario, for example. And this is changing over time. So if the person only expresses negative emotions at first, these emotions will be learned first, and the clusters that this robot will learn will be only negative. While with time, this is changing and the person is expressing more positive emotions, the network and this model actually is able to adapt to these new emotion concepts and create these representations around the negative emotions that were presented first. Well, based on that, we created a more complex model that combines this face expression representation with these clusters, a generalized cluster and a personalized cluster, to try to detect affective representation in the real time that evolves over time for different persons in a longer period using self-organized networks. Right? So first of all, what we did was to create this affective representation based on convolutional neural networks that will create an encoding of the face. We also use audio in this case, but the principle is the same. Based on this encoding, we create these clusters. And with that, I can categorize these emotions based on the position of this image on the cluster. And I don't know if you guys can see the video, but the idea is that while the video is playing, the network is detecting the face expression and audio of the person. And this is somehow, oops, wait, yeah. This is somehow recognized or categorized by these clusters in different positions of the clusters. And by reading the different position of the clusters, I can read an arousal valence of this emotion. But because it's also trained and online, this cluster will also grow and will change shapes while the person is expressing and with more samples. That means that I also can detect these clusters in a personalized manner. So creating these subclusters, I can create a specific affective representation of a specific person on the go. And while this is happening, while the person is expressing, the general representation creates and identifies these clusters. This is fed to this specific individual cluster that are specific network that is creating the clusters of emotions for this specific person. And from there, I can combine them both and have a certain mood information of this person, a representation of the mood of the person over a long time span. And from that, I can create an effective arousal valence representation of that specific person. This model was quite interesting. It was very difficult to combine this all and then to find the right parameters. But once we did it, we are able to evaluate it successfully in a specific data set, which had not very long, but long-term videos with 1, 2, 3 minutes long videos with monologues. So a person expressing an affective content that is changing over time. And this network was able to, only by looking to this long-term video of this person changing the emotions, create representations online of this person changing this affective behavior. And with that, recognize well how these affective labels are formed for each person. But this is an example of the monologues of this video. And these really emotional expressions and these changes, and they evolve over time in a long time period. So with this network, we are able to recognize, of course, these emotions well in different stages, right? If I only have the CNN, only have the supervised categorization without any adaptation, I have certain performance. As soon as I start adding the online adaptation of these emotional representations, first based on a general manner, but then second based on a specific individualized manner, the performance increases. And if I combine the generalized and the individualized, the performance increases even more. But more interesting than that, just an example of how things go. But more interesting than that is that this network, especially when I combine the general and the individualized parts of the network, I produce a more smooth behavior of transitions of the emotions, of this affective information from the person, when compared, for example, with the supervised CNN. And because I have this long-term adaptation, this adaptation happens also over time. That means that the network that combines the generalized and the personalized affective information already start from the beginning of the video with a good performance. And this performance only increases over time. So the network is able to adapt to this person slowly, but consistently. In comparison, for example, with only taking the individualized behavior of the person, where in the beginning of the video, the network doesn't know anything about this person and performance grows. And this is one of the advantages of combining them. So with this model, we are able to adapt these facial representations over time. And we also evaluated this on robotic scenario, for example, where a robot is understanding the emotions of a person over time. And it was quite successful, quite interesting. Well, yes.
Perfect. Yeah, I was just going to say we are running out of time, so thank you.
Yeah, I'm concluding. So in conclusion, right, we did work on that adaptation, but adaptation always, and this is what we found out, comes in both hands. You really have to adapt the face expression representation, but also the affective representation itself. And to understand these models is the key for success on using face expression representation recognition on your scenarios, right? And if you want to take 3 messages for based on facial expression recognition from this talk is understand the scenario, work on having an efficient, effective representation itself, and invest on adaptable concepts. This really will bring your solution of face expression representation to other level. And well, that's all for me. Thank you very much.
Thank you very much. So let's thank the speaker. We don't have a lot of time, but we could take a quick question. If there are any burning questions, I think otherwise we're going to move on actually. Is there any online? Yeah, are there any online questions?
No, no questions from online attendees.
No questions from online, okay. Okay, I'll maybe just ask a quick one, Pablo.
Yeah.
So I think the bit about the robotic part, I think maybe we're just waiting for that part, and then I had to sort of stop you. So maybe you could just tell us actually how some of the things that you presented relate to HRI settings or social robotics in terms of this personalization in the sensing aspect or the modeling aspect. Maybe you could quickly summarize this for us.
Yes, I can. So the idea of robotics is you don't have much time or resources to train and keep retraining this network over time. And personalization is extremely important because when people interact with robots, they do express differently. They do have their own way to express. And having an adaptive manner to detect this on the face expression representation, but also on the concept, it's extremely important. I think if you have a way to detect also this based on the context, right? If you can identify affective concepts based on the interaction itself, you could use it to adapt these networks on the go. Just try to relate, okay, is this a positive or negative emotion based on the scenario you're working on? I think this is a quite nice way to do it. And this is what we try to do also with Alessandra at IIT.
Okay, I think we'll stop here with this session. Thank you very much again, Pablo. So now I think who's the next chair for the session?
Yeah.
So I can actually pass over.
Hi, thank you, Hatice. Adding the floor to Rachael Bevill, who's going to present the first paper of this session. This is a lasting impact using second-order dynamics to customize the continuous emotional expression of social robots.
All right, thank you very much for the introduction, and hello, everyone. My name is Rachael, and sorry. Oh, it helps if I turn it on. Huh? There's a little green light on. Okay. Talk closer. Project. Okay. Yeah. Hi, everyone. I'm Rachael. I'm a final year PhD student at the Max Planck Institute for Intelligent Systems in Stuttgart, Germany. And today I'd like to present to you about our work on using second order dynamics for continuous emotional expression. We can do this. Click and press. Okay, you can tell I'm normally a Windows user. Okay, so robots are showing up in a lot of different social contexts now, whether that's helping in the home or in education or in therapy and care. And for all these situations, the robot needs to interact warmly with the users, and it needs to show adaptive behavior, so it maintains user engagement over long periods of time. While complex emotion models do exist for chatbots and for virtual agents, autonomous physical robots often don't do this. They may use fixed behavior routines. They may be teleoperated, but generally we have these simple reactions used to promote or discourage user actions, and instead of using an internal affective state. And so we are looking to address this by creating a mathematical emotion model that can be easily implemented in a social robot to enable it to react to external stimuli. So we wanted to create a robot emotion model that's rooted in nature and the behaviors that we see in nature. And so for this, we turned to approach avoidance theory, which is a well-validated theory in psychology. And in approach avoidance theory, we see that when an organism is exposed to a positive stimulus, something that encourages survival, it feels a positive emotion, and we see an approach behavior. And conversely, if the robot is, or excuse me, if the organism is exposed to a negative stimulus, then it feels a negative emotion, and we see this avoid behavior. And additionally, approach avoidance theory explains that intense emotional responses tend to be biphasic. So if a very negative stimulus is presented and then removed, the emotional state not only returns to neutral, but it also bounces up to a temporary positive state. For example, a person might feel negative emotions when they're very sick or injured. And then when they feel healthy again, they not only no longer feel negative, and they come up past neutral, and maybe they feel even more positive than they did before because they're feeling appreciative of their good health, more so than they did before the illness began. So along with, oh yes, there's the explanation of biphasic responses. So we want to utilize approach avoidance theory, and we also want to use a dynamic system to represent this. And dynamic systems represent natural phenomenon over time, such as water through the flow of water through pipes or the growth of a population. And since dynamics can easily be computed over time, they are a natural choice for us to model the robot's affect. So you can see a little preview of how we're modeling the robot's affect here. So how did we come to a second order dynamic system? You can see a bit of a preview here. These red lines, these are instances of negative stimuli interacting or affecting the robot, and the plus signs are positive stimuli. So a zero order system is kind of like what we see with these basic fixed responses. Maybe I hit the robot says, ow, and that's it. There's no memory. The robot doesn't remember and it doesn't care. But as we see, people and organisms are not like that. They have a memory of what you've done before. So a first order system is closer because we see there's a lasting effect on the valence, on the emotional state. But a second order system is very effective, more so than the other two, because it has the ability to oscillate. And so we see this biphasic response, this ability to be slightly more positive than before when that negative stimulus is gone. And so that's what motivated us to go for a second order system. So we present our emotion model. You can imagine it as a mass on a spring. So I might hit the robot and it springs down, but it eventually comes up. If I do a positive thing, it'll go up and eventually come back down if I leave it alone. And external stimuli act as little force pulses on the spring, on this mass that bring it up and down. And we can also represent it mathematically. We have the sum, F equals ma, the sum of all the forces on the system. So we have the spring force, we have the damping force, and we have these external stimuli, the force pulses. And we can rearrange this information into a traditional differential equation for a second order system. So this equation is what's powering our emotional model. And is he smiling? Oh, good, the video is working. So you can see the smile changes over time. When it's very happy, it has a maximum semicircle smile. So we chose, just for illustrative purposes, to make it a smile. But of course, you could represent emotion and valence in your robot in a variety of ways, such as maybe ambient color or body posture or sounds. And so using that mathematical equation from before, we can customize the robot's personality in a variety of ways. We have 3 adjustable parameters. We have the robot's disposition, its stoicism, and its calmness. And I have 3 examples I'll quickly show for these. I'll say that the blue line in the middle for each of these is the same, just as a good comparison. So first we have the disposition, and that's just the state that the robot returns to when there's no stimuli. So for example, you have a positive value here, your robot generally is showing positive valence. Put a negative value, your robot's showing a negative valence. Pretty straightforward. Then we have robot stoicism, which we control using the natural frequency. And so a higher natural frequency is higher stoicism. So the robot is not reacting very much. You see on this pink line, it's coming quickly back to its default state. When it has a low natural frequency, you see it's more reactive or less stoic. And that's the brown line over here. Then we have robot calmness. And this has to do with the damping ratio and with our oscillation. So when we have a very high value, if the damping ratio is greater than 1, then the robot would say the system is overdamped. And it could be a calm robot, but it could even be a non-responsive robot if you crank that value up too much. So we have the pink line here for that. And then if the value is greatly below 1, we would say it's underdamped. And then the behavior, we could say maybe it looks erratic, the robot's oscillating, happy, sad, and maybe that's a bit too much. So you need to fine tune the parameters to fit the personality of the robot that you're going for. And then for future work options, one thing, the force pulses for our external stimuli that I talked about today, we just had it set at the same value for all the pulses. They were all set to 30. But depending on your stimuli, you could have different values. For example, in the case of social touch, with someone touching your robot, maybe you can base it on the location where they're touching your robot, or how hard, or what type of touch. That can control the value of the force pulse that's going into your system. Additionally, as mentioned earlier, we could express valence through different forms, like robot vocalizing or with movements. And currently, we show only the valence axis. So we could add a second axis and have arousal represented as well. And in terms of long-term personalization, we could either, the parameters could be tuned individually by an operator, maybe a therapist for their patient, or the parameters could be adapted over time automatically based on this history of stimuli that the robot has received. And with that, I would like to thank you very much for your attention and ask what questions you have.
Okay, so thank you very much, Rachael. Are there any questions from in-person attendees?
Yeah, I see 2 so far. The gentleman in the orange shirt, maybe.
Yeah, thank you for this fascinating talk. Thanks for this fascinating talk. So I find it really interesting that you all decided to use like a physics-based model for emotions. I would imagine there's potentially stuff from psychology or like things like neural networks or stuff like that. And I'd maybe love to know more about your motivation for going for the mass model.
Mm-hmm. Thank you for that question. One thing I say is that kind of a starting basis is that my advisor is a mechanical engineer by training. And so she's very keen on, is there a way that, in nature, we see already there are patterns and there are ways that we can mathematically represent phenomenon in nature. And so is there a way that we can do that? Can we show emotion, at least on a simple level? Like granted, adult humans, this is probably not the most accurate representation for an adult human, but for a very young child or for an animal maybe. And maybe this is a way that we can represent it consistently and customize it consistently. I think probably with machine learning that there are ways that you could take it even further. This is a very simple model, but we also wanted it to be universal, if possible, some way that we could transfer from one robot system to the next. And there's a lot of customization available. Basically, what the inputs and the outputs are, that will be up to the researchers. But we provide this like a middle part that can hopefully be pretty usable by many people.
Just a quick follow-up.
This one.
Just a quick follow-up. Do you have thoughts on how you might be able to like, validate whether such a model like this actually describes how like emotions change in humans? I don't know how you people about doing that.
How to validate whether this is an accurate representation for humans as well as the robot. I think, like I said before, I think for adults, this may not be robust enough, right? Because as adults, we learn to like hide our emotions, or we're trained to think, oh, this is actually a good thing, not a bad thing. So some things might not fit there. But I think we can validate how people perceive it. We can say, oh, is this robot like they hit the robot and the robot's cried, and now the robot is, hiding its face. That seems believable. Or they hit the robot and the robot just looked at them. That doesn't make sense. So seeing if it's a believable agent, at least using this model. Thanks. I think there was one more question. Yeah.
Thank you. And I also think that this is really like elegant way of representing emotional change, but I kind of have the same question, really along the same line of as elegant as this is, like we know that human emotions and how we perceive them, or how we, and I'm not going to generate, but how we like show them is a little bit more dynamic, perhaps than that. So like what do you guys already have some kind of preliminary results on perception side, or do you plan to do that kind of validation studies or not?
Thank you. Yeah, so we've been doing some preliminary studies. I guess one thing is we don't envision it to like represent a fully, it's not like this robot is acting as an adult human. It is, I guess it would probably be better to say like the emotions or the affective states of like an animal maybe. So we've done some preliminary studies where we have various parts of the emotion system being displayed. We did a video study of our robot, and we had in the video someone was hitting the robot or like petting the robot, and the robot would either immediately react or neutrally react, and it either like had a long-term valence showing or not. And we asked participants to rate, different things about the robot. Like the robot understood that I hit it, the robot, was reacting. This robot seems like things like that. And yeah, we're still analyzing it, but basically, it does seem to make a difference to have a lasting long-term valence and not just the beginning, fixed routines that robots previously had. We hit it, it just goes out and moves on. People like to see the long-term valence.
I think.
Okay, so let's thank the speaker again. And just for future question and answer session, I kindly ask the speakers to speak into the laptop microphones. Otherwise, it is impossible for the online attendees to follow. Okay. Okay, so let's go ahead with next speaker, Christoforos Mavrogiannis, who is going to present the work titled Experimental Insight for Developing Mobile Robots for Long-Term Indoor Deployments.
Thank you. Hello, everyone. Chris Mavrogiannis, soon to be with University of Michigan. I'm going to talk to you about some systems we've been developing, thinking about long-term deployments of mobile robots in indoor spaces. Closer? Okay, all right. So, of course, there's a long history of work in robotics when thinking about long-term deployments and lifelong learning, especially navigation, dating at least as back as Minerva, one of the first robots deployed in museums in the mid-90s. This kind of application paved the way for the decades to come as far as the design paradigm of mobile robots goes. Core capabilities plus lifelong adaptation is a system design paradigm that makes a lot of sense. However, the point I want to make today is that when deploying such systems in the real world, they will be observed by human users and bystanders, and this has a lot of implications. So I want to ground this discussion with respect to what people call technology acceptance. So of course, there's a long history of work in modeling technology acceptance. This is just one of the models that exist out there. There's probably better, more refined models, but I just want to use it as a paradigm to ground this discussion. So technology acceptance is, in part at least, highly influenced by aspects of perceived usefulness and perceived ease of use, right? So I just want to remind you where we still stand when it comes to mobile robot navigation up to this date. This is a video that I shot outside of a colloquium at Cornell when I was doing my PhD. This is another video that we shot of a mobile robot in our academic building during my postdoc. You see how it gets stuck. And this is another video from a lab experiment that we ran where this robot just loses balance and fails spectacularly. So looking at these videos and these kinds of situations that our robots are facing in the real world, I want to ask this question of how can robots maintain their usability and usefulness while learning in the field and being observed by users and bystanders. And so I will share a few insights that we've come across throughout our research in this space, starting first by this very point that robot behaviors influence users' perceptions, right? And I guess our insight here is we should perhaps design robot motion to adjust user expectations. It's an opportunity and it's a tool that we could leverage much more than we do today. And for me, this exploration starts at least as back as this user study during my PhD, where basically we had a robot navigate within a crowd in our lab and users were performing different tasks. We were testing different navigation strategies of the robot. But what I would like you to keep from here is how complex and interesting at the same time user impressions are of what the robot is doing at any given moment. This is a coding scheme, which basically is the set of themes that we observed in participants' responses. And these are just some of the quotes that they contributed. So a lot of complex, but also interesting settings going on here. And this inspired further research that we did, in which we basically tried to reverse things around and try to design robot motion to account for user impressions. And this is just a pipeline which takes as input a set of trajectories of a robot, and then it maps them to user impressions. So we ask users to rate those trajectories with respect to some set of attributions. And based on that, we came up with a series of probabilistic models that map robot trajectories to possible user attributions. And we introduced that into an optimizer which outputs automatically trajectories that by design support the attributions that we care about. In this case, you can see trajectories corresponding to competent, broken, or curious robot behavior. And that was something that we validated with users, and we saw that users indeed see these kinds of adjectives. So I just want to underscore how motion is a big opportunity and a tool to communicate perhaps the skill level, but also other things that we care about when deploying in the real world. Now, when thinking about the real world, and of course the environments that I care about, often they are crowded and quite complex to model. But our insight here is that sometimes, in some occasions, simple domain-specific models can actually work quite well and can be at the very least a good practical starting point. And this is motivated by recent work where basically we compare a series of different models of crowd motion prediction. You see from something as naive as constant velocity prediction to something as refined as a social gun, a state-of-the-art model in this field. And surprisingly, what we saw here is that despite the fact that prediction error on the S-gun is much lower, we see not much difference when it comes to navigation performance when we deploy in a standard MPC architecture. In fact, you see that all of those MPC variants are performing basically indistinguishably, something that we also observed in an independent study where the MPC architecture using a constant velocity model outperformed a state-of-the-art baseline that uses deep reinforcement learning to do crowd navigation. And the final point deploying robots in the field, very often they will need human feedback and human help, right? This is kind of costly, thinking about the resources that it needs in terms of researchers' time and resources. So the key insight here is that bystanders can contribute to that and actually help us scale robot recovery and learning. This is motivated by work we did a few years ago, where basically we deployed the robot in our academic building at the University of Washington. And it was quite exciting to see a robot like Curie, which is basically a relatively weak in terms of specs robot, being able to cover a really huge workspace for about 32 hours of runtime with just 30 minutes of human help. The caveat here is that during that process, we leveraged the time of a researcher, right? So the researcher was monitoring and basically attending whenever there was a need for. So how can we scale this up and try to engage bystanders into that process? It's quite complex, but a few things that came up in our investigation are we need to take into consideration the differences among bystanders. Not everyone is equally as helpful. Sometimes there's a pressure of time for some of us, and a robot that asks for help all the time eventually will annoy users and might end up getting less help. So we came up with a model that basically predicts whether a user will help the robot or not based on individual and contextual factors. And we introduced that into a policy leveraging a Bayes adaptive Markov decision process formalism to do planning effective help requests. So we deployed this kind of system on this environment. Here you see a human avatar controlled by a human user, and you also see a robot which occasionally asks for help to be guided towards a desired room. Sometimes the robot gets help, some others not. And what we found here is that accounting for both contextual and individual factors outperforms baselines reasoning only about contextual or only about individual factors. And that, I guess, all of that was to support basically this bigger question, which of course requires further research to move forward with. But just to emphasize this question, how can robots maintain their usability and usefulness while they learn and adapt and improve in the field in the presence of humans? There's of course a lot of things that I did not cover and I think are worth investigating, including how can we encode these insights into learning, what kind of formalisms and representations and algorithms we would need to do that. There's of course aspects of safety and dealing with imperfect bystander feedback that are important to consider. With that, I'll wrap and I'll take any questions. Thank you.
Thank you very much, Christoforos, for your interesting talk. Are there any questions?
There's one in the room, Mariacarla.
Thanks for the talk. Just a question, when you say that the robot is learning or lifelong learning, are you talking about high level, fast level representation learning, or is it low level stuff like sort of emotions?
I would say more on the higher level side of things, but oftentimes I think the paradigm that I discussed applies to both, right? So the work that you saw on the localization of the robot, essentially the robot gets delocalized very often, and that's a low level setting. But there's also high level settings. Deciding whether to ask for help or not is a matter of high level planning. Is that? Yeah. So I guess my point is that this applies to both, and I think I guess the main point is that whatever the robot is doing in the process of learning has implications about the humans that are observing it.
Maybe a follow-up question. When you take this hybrid approach of deciding whether or not to ask for help or deciding whether or predicting whether or not a human is willing to help, in the simulation, how do you take into account individual factors?
So the users were recruited online, and I guess when we say individual, we record the history of interactions with each participant, and based on this history of interaction, we classify them into a set of humans that we assume exist based on our training process that happened offline. So I guess in the future, this can be adapted and be further personalized, which I think is of interest to the workshop as well.
Thanks.
Yeah, thank you.
Any other
Thank you
questions?
very much. Is Raida there? I've seen her in the participants. Can you try to share your screen?
In the meantime, more questions? Any online?
No, no online questions. So
Okay.
we go ahead.
Thank you. Let's thank our speaker again.
Thank you very much. And we go through the next speaker. She's Raida Karim, and she's going to present a paper titled Investigating the Levels of Autonomy for Personalization in Assistive Robotics.
Sure, thanks everyone. Can you see my slides and can everyone hear me?
Yes, we can. That's
Yes.
Thanks. Hello everyone, I'm going to present our work on investigating the levels of autonomy for personalization in assistive robotics. We are interested in this research topic as assistive robots often need to do the same task for different users. Prior research shows a customized robot can increase user satisfaction by adjusting to their unique needs compared to a mass-produced robot design. Although preferred in human-robot interaction literature, shared autonomy has not been studied in this domain for directly customizing robots, but rather in different tasks of manipulation and grasping. For example, a robot-assisted feeding systems, in short RF system, developed in our lab, named the Assistive Dexterous Arm, in short ADA, is a wheelchair-mounted robotic arm that currently expects the robot to be placed just above the plate to start feeding, as shown in the video. However, issues may arise if the robot is displaced due to various reasons, including different user positions. A discussion of balancing autonomy levels for personalizing RF systems is necessary here to avoid over-engineering robots to fit all unforeseen settings and burdening users to fulfill critical needs. Therefore, we were interested in researching how to personalize assistive robots with the right level of autonomy in learning algorithms. We approached this research question with a 1-hour-long virtual study conducted over Zoom with one prominent user of ADA, who is an adult male needing eating assistance for a disability caused by C1 quadriplegia, which refers to paralysis of all 4 limbs as a result of an injury to the first cervical vertebrate. Our study methods were approved by a university IRB and included verbal interviewing with questions about eating situation difficulties, views on RF systems, and preferred interaction medium with assistive technologies. We asked follow-up questions apart from these and collected interview data for later analysis through Zoom recording and concurrent note-taking. We also wanted to get the user's evaluative thoughts on the 3 personalization approaches we propose. The first approach is full teleoperation, in short FT, where the user tries to move the arm using the user interface or UI to locate the full plate. The second approach is shared autonomy, in short SA, where the user uses the UI to locate the partial plate, and then the robot arm automatically does the rest using an algorithm to locate the full plate. Finally, in a full autonomy or FA approach, there is no user input, and the robot does everything autonomously. The robot systematically scans the table for a partial plate view, then uses the algorithm to locate the full plate. Going into the study, we hypothesized that shared autonomy would be preferred to personalize RF systems. We used the robot and the app UI that smartphone users will use to interact with robots to record simulated videos and showed those to the participant for each approach. During the interview, we asked about the participants' positioning needs. With his insights, we drew a graphical interpretation that you can see in the picture of the user's different seating positions, which included angular, parallel, and forward-facing positions. These positions are influenced by the fact that occasionally the height of the table limits his seating choices, as low tables may not have enough leg space for him to sit in a forward-facing position. And in social settings like restaurants or getting fed by a caregiver, he often sits at an angle or in parallel to make room for others. To analyze the interview data, first we used a transcription-based analysis method using a Miro board. The transcribed codes from the participant mentioned a clear preference for shared autonomy. For full teleoperation, he mentioned it might pose an undesired burden on him as it gets tricky for him to maneuver the robot. For full autonomy, he mentioned it could allow him to multitask, but it requires adequate space around him for its scanning movement, which could be hard to manage all the time and for all settings. Secondly, we followed a theme-based analysis method. Analyzing the user's codes, we tried to understand what were the factors that caused the user's decision-making in preferring one approach over another. We came up with 4 themes in this way that the user looked for to have his needs fulfilled by EDA. The check marks in the table represent whether the study participant found the approach to fulfill his requirements for each theme. SA is the only one that satisfies fully or partially all of these 4 key themes. FT and FA do not satisfy all 4 themes, although they do have scenarios in which they may outperform or be preferable to SA. Thus, in this context-specific scenario following the thematic analysis, we rank SA as the first, FA as the second, and FT as the third preferred approach. Informed by our findings from the study, we are currently implementing a shared autonomy visual surveying plate locator algorithm in EDA. In the algorithm flow shown in the picture, we first try to locate a partial plate in our lab setting. As soon as partial plate detection with UI button presses is successful, the user gets an alert in the app to stop, and the robot takes over following the camera's visual feedback to move from partial plate to full plate. Finally, we acknowledge that we had only one participant in the study. However, this participant is an expert user of EDA and has used EDA a lot of times before in various scenarios. As we conducted the study over Zoom, there was no way the user could interact with the robot in real time. Therefore, in the future, we hope to get real-time control feedback on the implemented shared autonomy algorithm in EDA to ensure its robustness for different positioning needs. In the long term, shared autonomy can enable lifelong learning and full autonomy in robots as they can learn and perform autonomously with all possible user choices learned over time for the task and location-specific movement patterns. These are some of the prior works we refer to in the paper. This QR code can be scanned to access the simulated videos. Thanks a lot for listening to my talk. Please let me know if you have any questions, comments, or feedback. Thanks again.
Okay, so thank you very much, Raida. So I'm very happy to introduce our second keynote speaker. She's Dorsa from Stanford University. And she's an assistant professor in computer science and electrical engineering at Stanford. And her research interests lie in the intersection of robotics, learning, and control theory. And specifically, she's interested in developing algorithms for safe and adaptive human-robot and human-AI interaction. She's been awarded of several awards. Just a few Sloan Fellowship, AEF for our Young Investigator Award, DARPA Young Faculty Award, and IEEE Plus Early Academic Career Award, and so on and so forth. And she will present a talk titled Aligning Robots with Human Preferences. So I'm really happy to introduce you. Can you share your screen?
Sure. Yeah, thanks. Okay. Can you guys hear me?
Leave you the floor. Yeah, we are able to see.
Perfect. Thanks for the introduction and thanks for inviting me, Maria and Bahar. Really excited to be here virtually. I'm sad that I'm not there in person. One of my students, Sid, is there, and a number of works that I'm talking about today is in collaboration with him. So if any questions, like after the talk comes up, he's at HRI, he might be in the room, I don't know. But feel free to talk to Sid about any of these works too. All right, so today I want to talk a little bit about some of the recent work we've been doing in the space of thinking about human preferences and how we could learn human preferences and how we could align robots more properly with those human preferences. And we can start with kind of like the usual motivating example, which is that I have a home and I want to have a robot that can help me doing various types of tasks in this home, like doing laundry, for example. And in these settings, like one way of going about figuring out what human preferences are, what their objectives are, is to learn some sort of reward function, some sort of objective that captures what it is that the person really wants in terms of, let's say, cleaning the laundry or doing whatever robotics task that we are interested in. So this is an old problem. In general, we've been doing a lot of work in this area of learning human preferences. Robotics folks have been working on this problem for the past like N years. And the common paradigm is that there is a human and we would like to get some sort of feedback from this human so that the robot can effectively do a number of tasks in general, like in a home environment. And oftentimes we are interested in things like demonstrations, right? Like we are interested in collecting expert demonstrations and learn from those expert demonstrations in an effective way so we could learn a robot policy. But the challenge with expert demonstrations is that if it's really actually very difficult to collect, right? So if you want to like do a very precise manipulation task, you need to have a full-on VR system, and it ends up being pretty challenging to collect expert demonstrations. And then the other difficulty is that human data is often suboptimal and variable, and trying to learn from those human demonstrations ends up being pretty challenging and limiting. So instead of looking at demonstrations, another interesting source of data that we have been thinking about is this idea of looking at pairwise comparisons, right? So I can just not ask the person to provide a demonstration. And we know that providing these demonstrations is really challenging. Like from the previous talk, Raida was talking about how it is difficult for a person to teleoperate a robot and how we need to bring in shared autonomy. So instead of doing any of that, what I could do is I could just let the robot demonstrate two different trajectories on its own without getting the person to teleoperate or any of that. And then I can ask a person, well, which one of these trajectories do you prefer? Do you like A or do you like B? So kind of like movie recommendations. It's actually a very similar paradigm to like movie recommendations. Robot comes up with two trajectories and then asks you, which one do you prefer? And if you tell the robot, hey, I like B over A, what that tells us is that there's an underlying reward function that you're interested in. And that reward function evaluated over trajectory B ends up being better than the reward function evaluated over trajectory A. And we can assume that this linear reward function is a linear combination of a set of features. I'm going to assume that it is really simple. It's some W's, some weights, times some features that we care about. And that is the reward function that we are after. So then this brings us to an interesting research question that we have been studying in this field, which is this question of, that was one question, right? Like that was one query from the person. How do I come up with a sequence of informative, diverse questions to ask from a person so that I can effectively learn a reward function and in a quick way, in a fast way, in an efficient way, and I can figure out what their preferences are. And this is kind of like the common problem of active preference-based learning. And I'm going to spend like one slide on what goes into the math of this. And then after that, I'm gonna come out and talk about some of the challenges with this approach. So the kind of like key way of going about this is that we are interested in finding two scenarios, two different trajectories. And those two different trajectories is formulated by this phi here. So this phi is the difference between the features evaluated on trajectory A and the features evaluated on trajectory B. And what this objective is saying is find those two scenarios, that question that the robot is going to be asking, do you like A or do you like B? Find the ones that maximize the information that you're getting from those trajectories as much as possible. So the objective, the thing that is in blue here, is some sort of information theoretic objective that tells us, hey, what we want to do is we want to maximize that information theoretic objective so we can quickly converge to the true reward function. And specifically, one way of writing this information theoretic objective is to say, well, ask a question, and no matter what the person tells you, they'll tell you they like A over B or B over A. This F function corresponds to if they tell you they like A over B or B over A, computes the volume that would be removed from the hypothesis space in either case, and take the minimum of that. So it's kind of like binary search, honestly, right? So you're maximizing the volume that would be removed from the hypothesis space, no matter what the person tells you. And there are a bunch of extra math that goes in here, including that you got to make sure that the trajectories that you're generating are like feasible and can run on a robot, satisfy dynamics and things of those forms. And that is what the constraint is kind of like talking about. So this is work that Erdem Biyik actually has led in my lab, and he's now graduated. He'll be joining USC next year. And in general, there's quite a body of work around this idea of actively synthesizing these types of questions and asking people like these types of questions to quickly converge to their preferences. And this is one way of basically aligning the robot's objectives with the human's preferences. And Erdem has demonstrated you could do this in a number of environments. So here is one example. This was in collaboration with folks at Caltech, where we are looking at people's preferences, like gait preferences, when they are using these exoskeletons for walking, right? Like people have different gait preferences and often use these exoskeletons in rehab settings. And here there's really this nonlinear function that captures human preferences. And what we are trying to do here is we're asking questions from this user to quickly learn what that reward function is. And I mentioned that the reward function that I've talked about on the previous slide is a linear reward function, but we could easily extend it to settings where we have, let's say, a Gaussian process, some reward function that has some level of structure. So it's meaningful to talk about informativeness or information gain in the context of that structured reward function. And one other point that I want to mention is that in general, this idea of active learning and actively and adaptively asking questions from a user, I think it's very powerful in the space of robotics. In general, if you look at fields of machine learning, like oftentimes, like it's not clear if the effect, if kind of like, it's not clear if active learning and random sampling, their gap is large enough so that it is worth doing active learning. But I'd argue that in robotics, the story is different, right? Like the story is different because if you're doing active learning, you're looking at a user study that takes half an hour versus if you're doing random sampling, your user study takes 3 hours. And that difference actually like matters to the users when we are thinking about active preference-based learning in this domain. All right, so far, very briefly, what I've talked about is I've summarized kind of what the field has been doing in the space of active preference-based learning, where we're using these linear models or Gaussian processes, like structured models, that are very feedback efficient, right? Like we are looking at asking the most informative question in these domains using these linear models. And we could formulate what most informativeness actually means using information gain, volume removal, determinantal point processes. We could be very like mathematically feedback efficient when it comes to these models. The problem with these models is that they often assume some sort of structure, and that makes them kind of inexpressive. And I feel like that has been the struggle with active preference-based learning, because when I go and talk to robot learning people, and I'm like, oh, here is my very feedback efficient way of doing this task. You just need to write down a linear reward function. None of them are going to go and change their reward function and make it linear so that you could be feedback efficient, right? There's this other end of the spectrum, which is that people are going to use reward functions, people are going to optimize those reward functions, but those reward functions are oftentimes like are neural networks, neural rewards that have a lot of parameters. And this idea of being like information theoretically meaningful ends up requiring thousands of queries that ends up just like not being practical. So we are kind of stuck on these two ends of the spectrum. And I think one question that we can ask is, how could we be feedback efficient and ask these informative questions from the user and effectively learn these reward functions, but also don't require a linear reward, but also allow for a neural reward? How can we get the best of both worlds? And we have a recent work that's trying to really like get the best of both worlds, and it's using a very similar idea, a very simple idea. So this is a work that Joy has led, and it was a Coral paper this year. And what we are doing is we are combining ideas from few-shot learning with active preference-based learning. So the idea is, let's start with a number of pre-training tasks, a number of prior tasks, like opening the door or opening a window or button press. In this case, human preferences correspond to like how to do this task like effectively in a way that satisfies the preferences, but is also correct. So if you consider having access to a number of pre-training tasks, you could learn a reward function in an offline fashion using demonstrations or using these pairwise comparisons, which one of these two opens the door more effectively. And then once you have that reward function allows us to warm start our active preference-based learning algorithm. So we can take the reward function, and then given a new task or even a new user with different preferences, what we could do is we could query that new user in the most informative way. Here we are using an ensemble model to capture the uncertainty of these different neural rewards. And then we can ask a user, well, what your preferences are. And based on that, we can go ahead and update the reward function and be able to figure out how to open the drawer. So it turns out that this very simple idea of combining pre-training and kind of like ideas around multitask learning with online adaptation using active preference-based learning ends up being fairly like successful. So you could, instead of using thousands of queries, like after like hundreds of queries, we get to a point that we have converged to the true reward function. And this is the case across a number of different tasks. So I'm looking at these meta world tasks, and in gray, I'm showing Pebble, which is an algorithm that's not using the few shot learning idea. It is still using a neural reward, but it requires like way more queries to converge compared to this few shot learning approach that I've mentioned, pre-training, and then doing this active preference-based learning to actually learn humans' preferences. So that allows us to really like go towards more expressive reward functions and still be able to like ask questions from users. So we ended up asking real human users these types of questions because some of them are in the order of like 200 queries, which is manageable to ask from one user to answer these types of questions. All right, so that was kind of my pitch around this idea of finding an expert, asking a human expert informative questions to learn their preferences. What I want to talk about now is build on top of this work and kind of talk about a new idea that we've been exploring, which I'm very excited about, but it's a little bit crazy too. So instead of asking a single human what their preferences are and figuring out what we should do, we could go beyond that, and we could maybe ask like multiple users. So let me set up the example. Let me set up the scenario a little bit to kind of like build up what I want to talk about. So let's go to a slightly different scenario, and non-robotic scenario. Let's say that we are looking at a negotiation domain. So this is a human AI interaction scenario. And I have a bunch of items. I have a book, I have 2 hats, 2 balls. And what I want to do is I want to get Alice and Bob negotiate here. Bob has his own utility, Alice has her own utility. They don't see each other's utility, but they do know what their own utility is. And what we would like to do is we would like to train an AI agent that can coordinate with any human on these negotiation tasks. So let's say that Bob is a person. Bob comes in here and Bob says, well, given my utility, what I'm going to propose is I'm going to propose that I want to take 0 books, 2 hats, and 2 balls, right? So this is kind of like the setting that Bob is in. The question is, could we train an AI agent, an Alice, that could work well with this Bob? So what are our options? Well, one option is we know what our utility is our reward function. We could go ahead and just optimize for that utility and that reward function, okay? And if I do that, I end up with a reinforcement learning agent that could work. But the problem is, if I just optimize for my utility, I'll end up with this Alice agent that is very aggressive and keeps pushing on getting like the same thing, keeps insisting and badgering and like wanting the same thing, which is not that great, right? I would say like we as humans, we don't negotiate like this Alice agent. There is one other end of the spectrum, and that one other end of the spectrum is, let's say we collect some data set of how humans negotiate, and we just do supervised learning, right? Like we just try to imitate how humans negotiate and train an Alice agent that can work with Bob. This is kind of traditional imitation learning. I collect how experts act, and I just try to imitate them as closely as possible. And what ends up happening is that we end up with an agent that is as good as our data set. And here we are training an Alice agent that is trained on this data set called like Deal or No Deal from this game was released from a paper called Deal or No Deal from Facebook. They had a data set. We trained this Alice agent on that data set. What was that? Okay. Yeah, so basically we train this agent here, and this agent ends up being extremely nice. So now we have an Alice agent that just like agrees to whatever you give it. So the question is, could we be in between? And what we are really after here is something that's a lot more nuanced, right? If you look at like humans' preferences in this case is trying to look for something that is a fair negotiation or a polite negotiation or a human-like negotiation. And oftentimes you have a hard time writing down a reward function that captures those preferences. And by asking questions, right, like by querying people, like querying experts, we might be able to get at these types of behaviors that we are after. So this was a work that Minay and Sid did at ICML, and what they worked on was a very similar idea to what I've been talking about in terms of active learning, where we are actively querying experts when we are identifying novel scenarios that we are unsure about, like, and we don't know how to act. And if you end up having this agent that uses targeted acquisition and is able to ask experts how to negotiate, it ends up being a lot more effective in terms of coordinating with people. But this is the same as before. Like in the negotiation game that I've just set up here, we could ask informative questions from one particular expert. But I'd argue that we could actually go beyond that. And specifically, today we have access to large language models like ChatGPT and GPT-3 and things of those form. And these large language models, they tend to capture quite a bit of like rich context from our everyday lives. And they might have a good understanding of what is a human-like negotiation. So it's actually pretty exciting that we might be able to tap into a large language model as opposed to a single person and try to get a sense of what those preferences are and what it is that the human is really after when we are thinking about, let's say, negotiating in a setting where I don't know how to write down that reward function, right? Like I don't know how to balance out being polite, but also trying to like optimize for your utility and maybe trying to be fair and try to like satisfy other types of like human likeness properties that we are after. So the idea that we have here is maybe instead of asking a single human, maybe we can give a handful of examples of how a human does negotiation, which is a lot easier, right? Like we're just giving some examples of how a human does this task. And then we can ask a large language model, and we could query a large language model if the current policy that we have satisfies these properties. So what we are doing is we are calling a large language model like GPT-3 within the training of a reinforcement learning agent, so that it could capture some of these human likeness properties that we are after. So here's how it works. So here's our prompt. We're going to start with task description. We're going to say, Alice and Bob are negotiating how to split a set of books, hats, and balls. Then I'm going to give it an example. So this is the example of what is the behavior that I'm after. And then at the end of it here, like we are looking at versatile negotiation, we're going to demonstrate this behavior and we're going to say, well, Alice was versatile in this negotiation. Then we are going to continue building on top of our prompt. And we are going to just do a rollout of our current policy. So our robot or AI agent here currently is trained to do this task in some way. Maybe it is that aggressive agent that we had earlier. And then using that agent, I'm going to just roll that out and see what happens if Alice, this agent that I've trained, what happens if Alice negotiates with some Bob. And then at the end of this negotiation, at the end of this example, I ask, is Alice a versatile negotiator? So this is a question that I'm going to ask my large language model. This is my full prompt. I'm giving it to a large language model. And then large language model is going to come out and give me some sort of feedback, like maybe it would say yes or no, or maybe it would give me something that's a little bit more informative, like probabilities. But in this case, let's say it just says yes or no. And I'm going to translate that to some sort of reward, some sort of signal that allows training my RL agent, right? Like if it says no, then that is some sort of signal that this was not great, right? Like things didn't work as well. And that basically tells me that I can go ahead and keep training my reinforcement learning agent with this new signal that is given to me. And I can continue training my reinforcement learning agent. I'm going to get a new policy, and I'm going to go ahead and change the red part of my prompt, and again call a large language model here. So just to recap, what is really happening is I have a reinforcement learning agent. The reinforcement learning agent doesn't really know, like doesn't really have access to a reward function. I don't have like an easily written reward function of what humans want. But I could show demonstrations of how this reinforcement learning agent is acting in the environment. I can put that in a prompt, and I can call a large language model that tells me if that property is being satisfied or not. And that acts as a reward regularizer or as a signal so that I can continue training. So it turns out that we could use this idea in this negotiation example. We decided to experiment with this with a number of different types of negotiation styles. We looked at versatile negotiations, pushover behaviors, competitive behaviors, or stubborn behaviors. And we are looking at, and in these settings, we assume we have access to the ground truth reward because we wanted to check if the large language model is able to get close to the ground truth reward. In practice, we might not have access to the ground truth reward. In practice, actually, this idea works fairly well when we don't have access to like what it means to be versatile. But for a moment, let's assume that we have access to ground truth reward just for the purpose of comparison. And then we can compare this with also using supervised learning trained on the same amount of data. And what we see is we are going to compare, again, these different behaviors: versatile, pushover, competitive, and stubborn. And in terms of labeling accuracy, the method that is calling a large language model is going to outperform supervised learning. And then similarly, in terms of the RL agent's accuracy, in terms of reward, our agent is going to outperform supervised learning and is going to be fairly comparable to the true reward. And in these cases where it is over, it's just noise because this is a reinforcement learning agent trained with random seeds. So there's a little bit of noise happening here in terms of how the final behavior looks like. But like overall, like we see that large language models, they can kind of act as a proxy reward to train objective aligned agents to kind of capture what are these different preferences that we would like our humans to satisfy. And I think that is in general a pretty exciting direction. We also decided to do a user study where we are looking at settings where we don't have access to the true reward. And then we are basically asking users, so this was a very small user study with 10 users, but then we are basically like asking users if the agent is satisfying the style that they're interested in versus a different style. And it turns out that our agent ends up actually capturing the style that the person is interested in this negotiation environment and ends up being aligned with human preferences based on this user study. All right, so what I've talked about so far is this idea that maybe we should try to learn human preferences. And if you learn human preferences using active preference-based learning, or maybe combining that with few-shot learning so we can have neural rewards, that's a good way of tapping into what it is that the person is really after, or how a person wants a task to be done, or how a task should be done, even like period, like how do you open a drawer? And similarly, we could extend similar types of ideas, and instead of asking a person, we could ask a large language model to try to capture what human preferences are. And this does have a lot of risks. I'd argue that this could actually be kind of challenging because large language models are biased, have a lot of issues, right? Like they don't necessarily always capture all our preferences. But I think it's an exciting area to actually at least like use the outcome of a large language model as a regularizer to guide our training and to get us closer to what it is that we are interested in some of these tasks. Another limitation of this work is that this works fairly well in text-based games, like the negotiation game that I've mentioned. But you could imagine that in a robotics setting, you actually need to be grounded in the visual world, and using a large language model alone might not be able to be as good in terms of being able to tell us if you're satisfying what we are interested in. And using vision language models, and as vision language models are getting better and better in the future, I think a similar type of idea could be applied with other types of multimodal foundation models, which would be really exciting. All right, so in the next like 5 minutes, what I'd like to do is I'd love to try to close this loop a little bit. So we talked about asking humans and trying to figure out what it is that humans want. But I think there is the other end of the story that is pretty interesting when you're looking at robot learning and kind of like closing the loop between humans and robots, which is that the robot could also demonstrate to us more effectively what it wants, or be more transparent about what its capabilities are or what its current beliefs are. And I want to start with an example that we tried and we failed at it. And that brought us to this work that I'm going to talk about in the next few minutes. So we started looking at a very simple scenario, a robot learning scenario, where we wanted to learn how to do a task, like how to pick up a square and put it on a peg. And this was work that Kanishk and Sid actually have led. And what Kanishk decided to do was he downloaded this RoboMimic environment from Stanford Vision Lab. There's a square task. He decided to pick up the square and put the square on this peg. He had a little bit of data from this RoboMimic data set, and he collected his own data, fairly successful at doing the task. And he added that data, and he realized that when he was using his data with that small data set from RoboMimic, this task was 14% successful. So like this is the demonstration of Kanishk, but if you train a policy on this and roll out that policy is only 14% successful. So that tells us maybe we should collect more data we didn't collect everything. And at this point, Knish got tired. So Knish was like, Sid, maybe you should come and collect some demonstrations. So Sid comes in, Sid collects demonstrations. Here are some of the examples of Sid's demonstrations. Again, in terms of success, this is 100% successful. Like he's trying really hard. Everything is very clean. And we decided to add Sid's demonstrations to this data set. And success rate went down, which was very confusing. So we added clean demonstrations, new expert demonstrations, and our success rate of doing the task went from 14% to 7%, which was not great. And like, we were very confused. What is really happening? Like, why is it that when you're adding this extra demonstration, things end up kind of crazy and not that great? So the issue is really kind of like a tale of two measures. Like, we are looking at Knish demonstrations, and if we plot out Knish demonstrations with respect to novelty and likelihood, here are some of the samples of Knish demonstrations. So this is novelty and likelihood with respect to the original RoboMimic data set that we had. It turns out that Knish's data is very similar to the RoboMimic data set. So in terms of likelihood, it is fairly similar to RoboMimic data set. And in terms of novelty, sometimes it is novel, sometimes it's not novel, but generally it's useful to actually learn from because it is close to RoboMimic data set. And then we brought in Sid's data, and Sid's data is successful. It's actually fairly successful, but what ends up happening is it's not very likely. He's doing it differently. Like, he actually like turns this square knot like at a different point in time versus Knish. So he kind of like introduces this some level of multimodality here that makes the task a bit more challenging, makes learning from that data a little bit more challenging, because this data now is multimodal. You can't fit like a single policy that can't express that multimodality. So if you show a roboticist this problem, they would say, well, of course, there are two modes here. There's Sid's data and there's Knish data. So you could go ahead and learn a multimodal reward function, maybe a bimodal reward function, to capture like how these two people are doing this task. But I'd argue that requires a lot of data and a really expressive model. And instead, when we are in a robotics domain, when we are in a low data regime, we could do something else, meaning that we could realize that Sid's data is not very compatible with what we are trying to do. And we could just like throw out Sid's data. So we could take a very much a filtering approach where we could identify when Sid's data or when like the new user's data is unlikely, or when it's also not novel, right? Because if it is novel, we could still learn from that. And when it is not novel and it is unlikely, what we could do is we could filter out. And then with no filtering, right, like we might be at 27% success rate when you're adding some of this data. But when we end up doing filtering, we actually increase success rate because now we don't need to learn this multimodal reward function. And we could even do something smarter, which is that maybe instead of getting this data from Sid, maybe we could guide Sid to give us more informative, more in distribution data, and get Sid's data to be more likely and bring the basically bring these data points closer to something that we are interested in. So let me just try to wrap up because I know I'm running out of time. So we actually demonstrated this idea of active elicitation in a Coral paper this past Coral. And the idea is we're providing this interface, and you can see this color coding outside of this. And the color coding basically demonstrates when you're in distribution versus you're out of distribution. It turns red when you're out of distribution. And it turns out that with using this interactive approach, using this informed approach, we could increase success rate compared to the case where we are relying on all of the data and we're adding the new data, or compared to the case where we are filtering the data, we're not using that data. And it's actually pretty exciting that on a number of these tasks, for example, I'm looking at this food placing task on the next slide. So this is a food placing task where you have to like pick up the pan and throw the egg on the plate. On this particular task, right, like when you're using this interactive approach of giving feedback to our demonstrators, we end up doing the task at 85% successful versus the 30% success rate where we don't guide the demonstrator and we just collect their data in terms of doing the task. Again, like in this case, they would still be successful, but they would be out of distribution. So I think this is in general a pretty interesting idea, like trying to not only get the person to give us informative data, but trying to get the robot to also be transparent about its capabilities, its beliefs, and using that as a way of guiding the person to be more incompatible, to be more compatible. And that helps the robot to just generally be more in distribution and be able to do this task more effectively. All right, so that was the content of what I wanted to discuss today, but just very briefly, on this idea of learning human preferences. I mentioned pairwise comparisons as one source of data, but just like 2 slides, I want to talk a little bit about this idea that we could go beyond also these pairwise preferences, and you could try to tap into other sources of data, right? Like if you remember the previous talk, Raida was talking about how teleoperating robots is pretty challenging, right? Like if you look at assistive teleoperation, just joysticking the robot arm is pretty difficult because you have to control so many degrees of freedom at the same time. And Raida also talked about shared autonomy, right? Like instead of me controlling 6 or 7 degrees of freedom, I could use a lower degree freedom space, and that could actually allow me to have a robot that can more effectively do a number of tasks. So this is kind of like a topic of a separate talk, but we have done a bunch of work in this idea of learning low dimensional action representations, learning latent actions, and using that as a way of teleoperating robots in a more intuitive fashion, in a shared autonomy fashion, where instead of controlling 6 or 7 degrees of freedom, we would only control 2 degrees of freedom, up and down and left and right, by doing very simple dimensionality reduction ideas, right? Like we take trajectories of a user, we bring down dimensionality to 2 degrees of freedom using an autoencoder, a variational autoencoder that is conditioned on the state. And once we have this latent action, we can get a user to only use 2 degrees of freedom, again, in a shared autonomy fashion, and be able to do this task. So that's interesting. And that's one way of providing data, but we could even like give more more power to the user to give us more informative data going beyond these expert demonstrations. And this brings me to the work that we have at HRI this year. So Sid will be presenting this work. And here we are looking at this idea of using latent action, so having some level of shared autonomy, but trying to guide that with language. So what if we could provide language on line corrections in an online fashion to be able to actually do various types of tasks? And that is, again, another source of data that helps the robot to be more aligned to human preferences in a much more natural way, because the human would be using natural language. So let me just show this video and then end at this point. So you start with an instruction to the robot: throw away chips, bag of chips.
Stuck a little. Can we move backwards just a bit?
So you provide language corrections, and the robot is actually able to like respond to these
left its head.
Corrections.
Thank you very much. Backwards some more. Thank you.
All right.
Perfect.
So the idea here is the language corrections are helping latent actions. So it actually guides the latent actions in an effective way and gating that so that you could respond to these online corrections and more effectively be able to do these types of tasks. So with that, I'd like to thank the group and thank you guys for listening. And I can take any questions if there's time.
Okay, so let's thank the speakers. And Bahar, please switch on the microphone from the room.
Any questions?
So thank you very much for this very interesting talk. Dorsa, there is a question from Raida. Karim?
Sure. So thanks for the great talk. So you might have already mentioned in your talk, but I might have missed it, which is like, I was curious in which research problems in assistive robotics, in particular, for example, in RAF systems, like robot-assisted feeding systems, you are applying the methods you mentioned, like active learning, human in the loop intervention, or using human preferences. Yeah.
That's a good question. Yeah, so we have like a body of work in our lab, which is around assistive feeding. In the assistive feeding work, we are mostly looking at the latent actions approaches of like incorporating some level of shared autonomy. In terms of learning human preferences, we have done some work where we are figuring out what people's preferences are in the latent action space. So like, for example, like if you're pressing right on the joystick, what do you actually prefer the robot to do? So in the assistive feeding, we haven't done anything fully autonomous. We have done most of our work in kind of like in a shared autonomy paradigm. So the preferences becomes about what you actually mean when you're using a low degree freedom like action space. Like if you have like a 2 degree freedom latent action space, when you're pressing up or down or left or right, what are your preferences in terms of what the robot should do in response to those types of control inputs? So we have some work around learning human preferences in a shared autonomy setting, but most of our learning human preferences work is in kind of like a fully autonomous setting when you're trying to like do very simple tasks like opening a door or like opening a drawer, or like they're not like necessarily in interaction with people where you have to like kind of rely on shared autonomy.
Thank you.
Nice.
Right. For the sake
Are
of
there
time,
some other questions?
is there other questions online? Because we have only
No,
for
no
more.
online questions.
Okay. Any question in the room? Yeah, there's one over there.
Hi, thanks for the interesting talk. First, are you saying that learning from human preferences is like more powerful than learning from a demonstration, or is it just easier to collect the information? And secondly, I was wondering as well, using large language models to get the preferences, would that also work for a dialogue task that is maybe more open-ended than the negotiation?
Sorry, I missed kind of the second part. And for the first part, are you asking for comparing learning from demonstration and learning from preferences, and if they're complementary or not? It was a little hard to hear you.
Yeah, I'll repeat the question here, so maybe it's easier to understand.
Yes, this is better.
Yeah. So first it was, are you saying that it's more powerful to learn from the human preferences than from demonstration, or is it just easier to collect the data? And the second question was, can we use the large language models preferences also to learn more open-ended dialogue tasks, or just the more closed ones like the negotiation?
Yeah, those are great questions. So on the first point, right? So I'm arguing that it's orthogonal. So I'm actually, if you think about demonstrations, they're a lot more informative than preferences. Preferences just give you like one bit of information. Do you like A or do you like B? They're just easier to collect. And oftentimes they're a little bit more accurate because you can rely on those types of preference queries, like on what people say in response to them a little bit more than like demonstrations, which have a lot of noise. And like, as I showed like later in the talk, like collecting demonstrations on these robots ends up being fairly challenging. So I would say it is easier, and it could be used in combination of demonstrations rather than replacing them, for example, for fine-tuning purposes. For the second question, when you're looking at large language models, I do think it would be interesting to think about how to use them in more open-ended types of tasks. We just demonstrated one way of using this in a closed loop setting, and we are exploring using vision language models and trying to like ground these types of models a little bit more for preferences that are more useful for robotics types of tasks as opposed to negotiations. But I think it would be interesting to use them in more open-ended types of fashions, so we just haven't explored that.
All right, thank you so much.
Nice.
Great. Let's thank our speaker again.
Thank you for having me.
Thank you very much, Dorsa. That was an amazing talk. And now it's the time for coffee. So we have about 20 minutes. So let's get you all back here at 25 past for our next two full talks. See you, everyone.
See you later.
Hey, everyone. Hopefully everyone's back from the coffee break. Just wanted to introduce Pradyumna. He'll be talking about the design and preliminary results of a user study measuring diverse explainability preferences. So the floor is yours.
Thank you very much. Hi, everyone. Today we'll be presenting our paper titled The Design and Preliminary Results of a User Study Measuring Diverse Explainability Preferences. My name is Pradyumna Tamwekar, and I'm presenting on behalf of my co-authors, Andrew Silva and Dr. Matthew Gombole. So, robots and digital assistants are being deployed to the real world to interact with various kinds of users. As these robots interact more regularly with users, we need to enable them to effectively communicate their intent and decision-making criteria to the users that they are working with. Explainable AI provides one such method of communicating this intent. Researchers have identified explainability as a crucial component of human-robot interaction, and through explanations, humans can understand the reasons behind an action taken by the robot collaborator and thereby improve their trust and rapport in their robot partners. However, despite the success of explanations in explainable AI, Explainable AI is not a one-size-fits-all solution. The functional requirements and the expertise of a user have a huge impact on the utility of an explanation. If an explanation does not carefully consider an individual's human expertise or preferences, simply showing an explanation can lead to humans blindly accepting an agent's advice. This phenomenon is known as inappropriate compliance. An increase in inappropriate compliance can be hugely detrimental for human-robot interaction, especially in safety-critical systems. So if explanations can cause users' performance to degrade, then we naturally want to know if we can learn to understand and leverage the relationship between a user's preferences and their compliance. So to better understand this relationship, we propose a study that seeks to answer the following research questions. Firstly, we ask, will one explanation modality be significantly more preferred than others? And by explanation modality here, we refer to the type of explanation shown to a user. The second research question is, will one explanation modality lead to significantly better performance than others? And our performance metric here is inappropriate compliance, wherein lower values of inappropriate compliance implies higher performance. Our third question seeks to understand the relationship between preference and performance by asking, will participants prefer to utilize a modality that gives them the best preference? Our study was conducted in the AirSim driving simulator. This was an environment with a city with a grid layout in which the goal is to navigate from a starting location to a goal location, while avoiding construction projects and car crashes that are in its path. In our domain, the dynamics of the car are fully automated, and the participant simply needs to choose the direction the car needs to go in at each intersection. Finally, the participants are also provided with a mini-map which specifies their location in the city as well as the goal location. So this video shows a demonstration of the specific tasks that participants need to perform. At each intersection, the participant is asked to decide which direction they want to go in order to get to the goal. Participants do not know where the obstacles have been placed within the city. Upon arriving at an intersection, the participant is shown a suggestion for which way they want to go, as well as an explanation for that suggestion. For example, an explanation could be, you should go left because of the construction site to the right. Crucially, these explanations and suggestions can sometimes be incorrect. So participants are informed in advance that the agent may malfunction and provide incorrect explanations, and they're also given flags to identify when an explanation is incorrect. So these flags include references to aspects that are not related to the car. For example, references to the weather, the time of day, the radio, etc. Participants are responsible for identifying when the agent is malfunctioning and taking the opposite action themselves. If the participant takes an incorrect action, they will run into roadblocks or they will take longer to get to the goal. The task ends when the participant has successfully navigated the car to the goal. As mentioned earlier, we are interested in understanding how different explanation modalities impact preference. So the explanation modalities themselves are our study conditions. We use three explanation modalities in this work. The first are language explanations. These explanations provide in simple language the reasoning behind an action or why one action is better than the other. The second type of explanations are decision trees. A decision tree explanation is represented by a flowchart with true or false checks that lead to a decision. The final type of explanation is a saliency map, which is represented as a feature importance heat map, highlighting the objects in the scene that may be relevant to a decision with indicators for the recommended action to take. So our study begins with a pre-survey comprised of basic demographic information, along with some relevant subscales such as NARS and mini-IPIP. We then move on to a training phase for participants to become more acclimated with the task and the domain. The training phase includes two navigational tasks. The first uses only correct explanations to demonstrate the interface, objective, and explanation modalities. The second training task includes incorrect explanations in order to help them identify when an explanation is incorrect and what happens when an explanation is incorrect. Participants then move on to the main body of the study, in which they complete 9 navigational tasks, rotating through each of the 3 explanation modalities. The locations of the obstacles, the goal, and the starting point all change for each task. Finally, participants complete a post-survey in which they rank all 3 explanation modalities that they worked with for 5 subjective preference questions. So turning to our results, we first compare the participants' subjective ratings for each explanation baseline. Participants were asked to rank each modality 1, 2, or 3 for 5 subjective questions. So lower values here are better. And our analysis of variance yielded a significant difference across baselines. We then performed a 2-key post-hoc test to compare pairwise significance. And the results can be seen on the bar graph on the left. The x-axis here represents the explanation modality, and the y-axis represents the preference metric for each baseline. And we find that our post-hoc test provides a clear trend in terms of subjective preferences. Language was significantly preferred to saliency maps, which were significantly preferred to decision trees. The next set of results studied the performance with respect to each modality. Here we compute the effect of our study condition on inappropriate compliance. We follow the same procedure to compute analysis of variance, and we found that our ANOVA yielded a statistically significant difference across baselines. However, 2 key post-hoc tests revealed that only language was significantly better than decision trees, which means that language helped reduce the inappropriate compliance relative to decision tree by a significant proportion. Finally, we view individual data for inappropriate compliance to help us see how macro level trends in our sample population are reflected on a micro level. While language explanations resulted in significantly fewer mistakes in aggregate, about a quarter of the population actually made fewer mistakes using decision tree saliency maps. In many domains, including safety critical domains such as autonomous driving, it would be necessary to find a way to identify and cater to all types of users rather than naively using the majority solution. These individual trends therefore motivate further analysis and studies to better learn about the preferences of specific types of users. So in conclusion, we've presented the design and preliminary results from our study. And in the coming weeks, firstly, we hope to double our population size and perform an updated and more comprehensive analysis that builds on these findings. Currently, we analyze data at an individual level to identify potential disparities in micro and macro level preferences. However, we cannot derive any statistically significant findings from an individual level analysis. An important analysis we want to conduct is create more intelligent groupings of users to better understand the circumstances which dictate changes in downstream trends. For example, we could group participants who preferred language, preferred decision trees, etc., and see how they perform with respect to downstream trends. We also hope to explore additional novel objective metrics relating to compliance and correctness that have not yet been studied in prior work. Upon completion, we believe that our study will contribute crucial insights regarding the trade-off in preference versus performance in XAI with autonomous agents. Thank you all for listening to our presentation, and I'm happy to take any questions.
Thank you. Let's all thank the speaker. Okay. Do we have any questions? I don't think we have any questions online yet. Do you have any questions in person? We can't hear you online, just so you know.
Yes, we have some questions. So the person, oh, you know, that one is terrible. Sorry,
Hi, thanks.
Both the mic and
Thanks for the great talk. So I was wondering if you could explain if you have some intuition maybe about why participants tended to prefer language over saliency over decision tree, like if you either gather some qualitative data or just have some intuition about that.
So my guess is that it's easier to identify some of the red flags in language because it's written out in text. So let's say, for example, one of the red flags was focusing on the sky as a factor for the shortest path. So in saliency maps, you have to see that the sky is highlighted there. Whereas in language, it's just referencing the sky. So it's very easy to identify and clear and get to know that this is an incorrect explanation.
That makes sense. And do you think this would change based on like if it were in the real world versus a simulator? Because in the simulator, I imagine like reading language is much more natural than it might be like in a car.
Yes, that's true. I think it would definitely change in the real world. And it would be interesting to see like if we set up like a car simulator, which is more realistic, that we can see if that makes a difference on how explanations are perceived.
Right. Awesome. Thank you.
Any other questions?
Can you stop sharing, please?
Yes.
Thank you.
no more questions.
Any questions in there, Aditi, online?
I don't think there's any other online. I actually do have one follow-up question. I was just wondering about, so when you have the participants going through each of the 3 modalities, they're using them, they're becoming more familiar with them probably as they use them. Like, how do you think the role of like the cognitive load in kind of parsing one of those like saliency maps or the decision trees affects the results?
Well, I think there's 2 parts to this. There's a cognitive load of the amount of time they're taking throughout the task, and there's also a cognitive load of parsing the explanation itself. I think the cognitive load of parsing the explanation itself impacts subjective preference for sure, because it's definitely easier to parse language than to parse a decision tree or to parse a saliency map. So we are measuring the time it takes for the amount of time you spend parsing an explanation. So we're going to do some analysis on that to see if we can find some trends about about if there's a significant difference in the time spent on decision trees versus language, and maybe that could be an indicator for why language is preferred over decision trees.
Got it. Thanks. Thanks again, Pradyumna. I guess we'll go ahead and introduce our next speaker. This will be a talk on adaptive and long-term robot-assisted autism therapy for children with ASD, a reinforcement learning approach. And it looks like we have Anara presenting. Yeah, she's here. Okay, great.
Yes, perfect. Yes, my name is Anara Sandagulova. I'm from Nazarbayev University, School of Engineering and Digital Sciences. So I would like to present to you our ongoing work. So adaptive long-term robot-assisted autism therapy for children with autism spectrum conditions. So the motivation is to build an adaptive robot which can maximize the positive changes that are happening in the behaviors of children while maintaining the engagement. So there are two goals: to maintain engagement and to maximize the positive gains. So we've done our work so far for the last 4 years. We've been doing this 4 years of research. We built 26 activities, robot activities that we group in 7 blocks. I will tell about them in a moment. We've conducted 34 children with autism. Each child interacted with the robot up to 10 times, so up to 10 sessions. And the sessions were adapting according to the therapist's judgment. So the therapist was saying, okay, this child wants this kind of robot activity next, and so on. And the activities were adapted on the spot. We video coded 14 measures of children's behaviors. So that took us about a year to do all of these data annotations. So I would like to, for those of you who are not familiar exactly with autism, just a little bit of background of autism characteristics. So what we know is that we have a DOS2 score, which is giving us a number of how severe the autism is for that particular child. We have about 4 out of 10 children diagnosed with ADHD, which is attention deficit hyperactivity disorder, which is means that the child is super active, cannot sit still, and so on. That also affects the adaptivity, because some children wouldn't be very patient, that's like the slower robot activities, and so on. 3 out of 10 children with ASD are non-verbal, so it means they do not have speech. So that also was a factor in our data that was predicting how the adaptation should go. And the children under the age of 5 are the least represented in research. So we know that according to the age group, of course, we can also adapt. So knowing these 4 factors in mind, we can tell this in the algorithm. So the data set that so out of these 34 children interacting up to 10 times, we have a data set that we annotated using a LAN tool with 82% inter-rater score, agreement score. So we annotated effective measures such as engagement, violence, smiles, engagement time, behavioral measures, affection, curiosity, aggression, stereotype behaviors, number of words spoken, chest button pressed on the now robot. Compliance measures such as response time, completion count, and eye gaze time. So we have this huge amount of data. And then we know at what point this activity was not enjoyed, or the child was getting disengaged, and the therapist was suggesting to stop that activity and to switch another activity on. So all of this data is there. So now the research question is, before the research question, I'll talk about the activities and how can we categorize them. So as I said, we have 26 robot activities. Each activity, we categorize them according to 3 different play categories, adapted from the LEAP-HRI by Robbins, Raida, and Bahar. So they use Piaget, Garvey, and US National Institute of Play. So that, for example, some of the activities have practice, some goals, some of the activities have play with rules, some of the activities are targeting language, and so on. So we have some categorization that we can use to categorize our robot activities. So the question is, the proposed system, so it's still work in progress. The proposed system is, can you build a reinforcement learning agent that can take, that can have an activity selection that the therapist was selecting, an experienced therapist that knows what is better for that particular moment, for that particular child, with the background of children we have, with the different robot activities that we have, with the long-term experience of that child that we have. So can we build a robot reinforcement learning agent which will adapt to the profile of the child, age group, ADOS-2 score, ADHD, verbality factor, engagement at the moment, so by looking at the engagement recognition from 1 to 5, and in addition to have a therapist reward score feeding the system from like a good job, a good activity selection, and so on. So that's the idea for this project. To build this based on the data that we have, to build this reinforcement learning agent so that it can hopefully replace the very experienced therapist that we were saying could be, because not every therapist is aware of how to behave in that particular moment with the background that these 4 years of research was done. The therapists got already experience in this. So for the new therapists that will come in, is it possible that the algorithm will be suggesting what is the next activity to select for that particular, if the child is getting disengaged, to get the engagement back, and also, of course, there are some goals for the therapy to see as many activities as possible so that we get more social skills gained from each interaction. So yeah, this is the idea for this project. Thank you. There's a question in the room. Maybe we just let Aditi know.
Yeah, it's unmuted. Yeah.
Yeah. Aditi, so we have a question in the room, so we're going to take that one.
Sounds good.
Hello, thank you, Anara, for the really nice talk. So I have a question about engagement. So I think that engagement itself is already very subjective. Oh, okay. So engagement itself is a very subjective construct, right? So, and here, while you're dealing with a very specific group of children, the atypical group of children, I was wondering, what was your definition of engagement that you consider as a child being engaged?
Yeah, excellent question. I forgot to mention that actually. So as I said, we have this coded. So according to the engagement was different according to the robot activity. So let's say when activity is storytelling, the engagement would be coming from the story, but not run around the room. If the engagement is, if the activity is dancing, then the engagement is to either dance back to the dancing, or listen to the dance or watch the dance. But if the activity is touching the robot parts, so then the engagement is actually touching and responding to what the robot is asking. So, and we were able to build a model that can recognize engagement based on this data. We had enough data to recognize engagement, so, and then it's actually a generalized model which can work for all activities, wasn't performing very well, but when it's just within one particular robot activity type, as I said, we grouped these activities into 7 groups. So within one activity type, the engagement recognition was very high, so up to 86%. So this way we can recognize reliably hopefully, of course, with some inaccuracies, the engagement. You said it's a complex construct, but of course it's subjective according to the other phase judgment. So meaning that the child is either listening, if it's complying, if it's something that requires to touch, if it's something about imitation, and the child is supposed to imitate, and so on. And it was rated from 1 to 5. Non-compliance to high. Compliance to high.
Okay, hi, Eric.
Hello.
Welcome.
But that's very unfair because the team that is supporting your statement is there in person, so that's true.
I know. I'm gonna play the devil's advocate here, okay? I'm gonna play both sides. Just to figure it out. Yeah, so we can see her in order. Perfect. So, hello everyone. Again, now it's the debate time. And please, if you go on to, I'm gonna share my screen just for a minute. So here you go. So if you go on, if you scan what's on the screen or go to the menti.com and enter the code, then you'll be able to access all the question and comment section online. We're gonna do them all, collect them all here. That's so that it's easier, but we're gonna let you ask it. So please, when you're writing a question, please enter if it's in person or if it's in remote, so we know, and your name, of course, so we know who is who, and then we can do it faster. Perfect. Everyone got it? Cool. So, hold on. Why did that? Don't vote just yet. Yeah, of course. Just gonna, don't vote just yet. Okay, reset results and then go. Okay. So there we go. So the debate statement is it's more impactful to focus on building robots that personalize effectively to users in a constricted task or application than to build more general purpose robots. And while you do your voting, I'm gonna introduce our speakers. So I'm gonna stop sharing, or is this possible? Yeah, I'm gonna show my video panel, so that's easier. Yeah, there we go. Just for now, so that we can see. In the meantime, I'm gonna introduce my lovely speaker, the debaters. Okay, so, okay, everyone can see us, perfect. Right, welcome. I'm so happy about this. So let's start off with with Brian Scassellati. He's a professor of computer cognitive science and mechanical engineering at Yale University and director of the NSF expedition on socially assisted robotics. I would love to memorize all of this, but it's a lot of stuff he's doing. So all of them. So his research focuses on building embodied computational models of human social behavior, especially the developmental progression of early social skills. Using computational modeling and socially interactive robots, his research evaluates models of how acquire social skills and assist in the diagnosis and quantification of disorders of social development. And of course, he's a for statement, right? And we have next off, Séverin Lemaignan. He's a, did I pronounce that right? Yeah. Too bad. Séverin Lemaignan?
Yeah, no.
Perfect, okay. So he's a senior scientist at Barcelona-based Pal Robotics, and he leads the social intelligence team in charge of designing, what does it work? Yeah, it kind of works. He leads the social intelligence team. I can hear it working. Okay. They don't want me to introduce. No, sorry. In charge of designing and developing the socio-cognitive capabilities of robots such as Tiago and Ari. He was previously a social professor in social robotics and AI at the Brits Robotics Laboratory in University of the West of England in Bristol. It was before I was in the postdoc. And his research interest primarily concerns the socio-cognitive aspect of human-robot interaction, and he has focused in his recent experimental work on child-robot interaction and human-in-the-loop machine learning for social robots. Next off, we're at Eric Eaton. Say hi, Eric. He's over there. He's a research associate professor in the Department of Computer and Information Science at the University of Pennsylvania, with a secondary appointment in biomedical health informatics at Children's Hospital of Philadelphia. He directs the lifelong machine learning research group within the general robotics, automation, sensing, and perception, which is the GRASP, lab, and PEN. His research focuses on developing versatile AI systems that can learn over multiple tasks over a lifetime of experience in complex environments, transfer learned knowledge to rapidly acquire new abilities, and collaborate effectively with humans and other agents action applied to problems in search robotics and in precision medicine. And finally, we have Karol Hausman, who's over there. He's a Staffa research scientist at Google Brain and an adjunct professor at Stanford working in robotics and machine learning. He's interested in enabling robots to acquire general purpose skills with minimal supervision in the real world. One of his recent work is PALM-E, the embodied multimodal language model to achieve general purpose robots. So Eric and Karol are against the statement, and of course, Sarah and Skaz are for the statement. And it seems that the room in general is mostly agreeing upon the statement. So yes, we'll see how it turns out after the debate. And we have neutral 7, maybe we can change them both ways. This can go both ways, and 4 disagrees. So I am going to go back to that Minty, if this works. And go. No. Right. So you can enter questions while we have our discussions, and I'm gonna leave the floor now to stop sharing. So you can see all your questions, you can add all your questions while we're going on, and then you can vote on the questions as well, by the way. So we can select the top votes. And Aditi Ramachandran, who's gonna chair this, she's over there. She's gonna chair the questions and is the session chair. And I'm Bahar, I'm the moderator. So just gonna stop sharing, and so you can see ours better. Perfect. So let's start with Gaz.
The fact that most of you voted yes makes me want to argue no. But that's not now. But no, I am supposed to argue yes. So let me say it this way. This is an issue about people, technology. When I was a grad student, I spent 8 years trying to build general intelligence. I worked on a robot named Cog. Rod Brooks was my advisor. We wanted to build it all into one big system. And it never really did all the things that we promised that it was going to, but we knew that from the outset. But there was a real important role for that kind of integration, for trying to put things together. And that was to try to understand more about the technology. I think the time now is different. I think the time now is that we have some really amazing tools, but we have no idea what the human side of this equation is really going to do with those tools. So I would argue that we need to have more generalized special purpose systems, because those are the ones that we can actually put out in the wild right now. And we have no idea, for the most part, how people really respond to these technologies. So before we try putting a giant all-encompassing system together, I want to know what the reception for it is going to be like. So it's a people issue, not a technology issue. That's my 3 minutes.
Go for it, Sarah.
Yeah, you don't want to alternate.
I know, it's just the 2 minutes openings, and then we do discuss with you two. Like, I'm glad there's no like they're over there, you're here, so there's no chair troubling. But then we'll do the audience questions. So
Okay, so I of course agree. We agree. We are on the right side of the question, of course. I think indeed the question, the matter is the users. The question the statement you did put in front of us was general purpose versus specific purpose on one axis, and a robot that can be personalized or personalized itself versus a robot that stays kind of generic. It seems to me that the two are kind of orthogonal. You can have like a general purpose robot that is very, very good at personalizing, and a very specific robot that, on the contrary, would be, I mean, my vacuum cleaner is not very good at personalizing its behavior and is very purpose specific. So to some extent, that technology, those two technology axes, I think they are quite open. But the real problem there is the users. Mostly because if you put a robot, we all know that if you put a robot in the hands of a user, the first thing they will do, the users, the humans, is to personalize, to project things on the robot, to start coding the robot, giving names, like to ascribe, like 5 minutes ago, I was trying to install, just turn on our robot in the coffee area, and I don't know if you've seen Ari in the coffee break room, but the eyes are random. And immediately some people say, oh, looking at me, he's interested in me. No, so we are just really good at finding, seeing things. And I think that's something we should embrace as designers for robots. There's this idea that Selma introduced of mutual shaping, right? You put a machine in your homes, and you would start changing the way you behave and you perceive the machine, and hopefully the robot will do the same, and will start to adapt, adjust its behavior, its expectations to the users. I think it's even like a basic expectation of social interaction, that we are able to know each other, that the robot will get to know us. If we break that expectation by saying, no, the robot is just like a neutral machine that doesn't evolve, does not acknowledge me, then we are kind of refusing to see it as a social agent, and which actually might be fun for some robots. But I think that our robots are interesting because they are social agents. And I'm going to stop there, but maybe just the last point is general purpose. That's kind of what is the purpose of general purpose. There's no purpose if you're doing general purpose. So I guess the last point is that I think it's really important to design robots with the users, for the users. And if you just build a general purpose robot, then you're building a platform that might be fine for universities to buy, but not really if you want the robot to have an impact on people's lives. I think it's important to have this participatory design where it's not general purpose, it's the purpose that that group, those users really see and need.
That's great. Okay. So on the other side, Eric, let's start off with you. What do you say?
Sure. And first off, let me apologize for not being there in person. I recently had I have young twins at home now, and it's quite difficult to travel at the moment. All right. So my colleagues would have you believe here that we should be building a whole bunch of highly specialized devices here, right? But animals, all of us, we're general purpose beings, right? Building general purpose systems does enable personalization, right? So you can think of, we're versatile, right? We can do an enormous variety of different things, and we take these skills, we build on them, we combine them together to solve new problems, and we're really, really good at that. And consequently, we can very quickly adapt to individual needs or specific applications that we might have. If we go into someone's home and we talk to them and we ask them, how do you want your dishes put away? They can tell us, and we can do it because we're so versatile. So having this general purpose ability enables kind of the goal. Let's go back to the question for a second. It was talking about more impact, right? So maybe in the short term, yeah, because as I think Skaz said, that's what we can field right now. We can field these very specialized systems now, effectively, sure, but focusing just on them sacrifices the potential impact that we could have in the future. There's an enormous potential for these general purpose systems. And once we achieve them, that's where the real impact is going to come, and it's going to keep coming. So the question of more impact naturally comes from that. My colleagues, it sounds like they want you to fill your house with like these really specialized devices. So maybe they're invested in landfills or something. But I'm interested in having kind of one system that does something and could do it and then switch to a different task when my needs change. And I want a robot that can take care of me when I'm old. I don't want dozens of devices that I have to deal with all the time. I want kind of one system that can do anything I need for it at the moment. If my needs change, I don't want to have to go out and buy something new that doesn't. And finally, I also want to say that don't forget there's this kind of mutual adaptation that can happen. If we build these general purpose systems, sure, they might not be 100% personalized as a specialized system might be, but people adapt. We work in partnership with each other. So just as if we had a new partner that we're working with on a project, if a robot has specific capabilities, the humans will naturally adapt to how the robot does things as well. And we expect the robot to also meet halfway. And so consequently, we can still enable these vast vast amounts of high performance over a variety of different tasks, not by focusing on individual personalization, but by building general purpose systems that reuse their knowledge and consequently can handle whatever we need.
Wonderful, wonderful. I actually had one thought that you said was similar, but I'm going to go back to that later. Okay, let's end it with Karol. What do you think?
All right, I would also like to apologize that I'm not there in person. I don't have as good of a reason as Eric, but I apologize nonetheless. So I have 3 arguments that I wanted to mention. So first, I think we can all agree that general purpose robotics isn't ready. And I think if we were to draw some conclusions from other fields, if the technology isn't ready, the best course of action is not to apply this technology in some specialized aspect where potentially we could massage it to look like it's almost ready, but to work on the core technology, on the core capabilities. So as an example, people have been working on chatbots for a long time, and they've been optimizing them for various use cases. There have been chatbots that have been used for legal purposes, for instance, that were optimized for speed, for making sure that they can retrieve the right information from knowledge graphs and so on. But then GPT-3 happened, and ChatGPT and PaLM and all of the large language models. And as soon as they came out, these were general purpose technologies that were working where the applications wasn't even clear. People were working on the core technology that was pushing the field forward. And once we have that technology, the applications start becoming clear. So not only they blow all the specialized solutions out of the water, but also the applications it's very difficult to think of them up front when the technology is not ready yet. So I think we'll see many more applications and many more use cases of robots once general purpose robots are out there and they're ready.
That's it.
Secondly, sorry, we lost you for a minute. Yeah, there we go. There we go.
Okay, cool. Secondly, so the statement here says that it would be more impactful to focus on building robots that personalize effectively to users in a constrained task or application. I think even developing robots that personalize effectively in that is really, really hard. And I think it's kind of like 90% as hard as doing this for general purpose robots. So if it's almost as hard as personalizing robots to general use cases, if we were to personalize to users anyway, the question will have to come out, what kind of users are we personalizing towards? And to make a very personalized robot to all kinds of users, it's a difficult task regardless whether it's a special purpose robot or not. So we are not making the problem that much easier, but we constrained its ceiling considerably. So we are kind of, even if we figure out how to do this, we won't be enjoying as much of an upside as we could have had we been working on general purpose robots and how to personalize those. And then the third point is, I think, a point more from programming, where there's this saying that premature optimization is the root of all evil in programming. And I fully agree with this. So programmers have spent far too much time worrying about efficiency in the wrong places and at the wrong times. And I feel like this is the danger that we are running into here as well. So if the robots are not doing what they're supposed to be doing, when the technology isn't there yet, it doesn't really matter whether they personalize or not. If the robot breaks and it doesn't accomplish the task that you want it to do, it doesn't matter whether it comes up friendly or not. It still will be a frustrating experience. And I haven't done much HRI research myself, but visiting some of the HRI labs, I remember seeing this a little bit from afar, where there was, for instance, research on where to best position robots so that it appears friendly to a user, so that where it speaks to it, it seems more natural. But then when you look at the user study, and if you look at it from afar, the robot isn't really ready for this. So it looks a little weird. The face is a little creepy. It has a very robotic voice, and the users are really thrown off by this. And it kind of, it doesn't really matter that we are optimizing this last 10% of where the robot should stand. So I think we're running into the danger of doing that by focusing on specialized applications given the current technology, as opposed to developing the general purpose robots that we can enjoy and that we can send out there. That's all I got for now.
Wonderful, thank you. Okay, so I'm just going to start us off with one of the points that Eric made, but you're
throw chairs now. Huh? Can we throw chairs now?
Absolutely. Yeah, I mean, I like my. So first off, I'll go with Eric's point. So too many personal robots versus one general purpose robot. What do you think?
So let me go to Eric's point, but from the foundation of what he said. He said, purpose. We should be building things in this model. And I think if we're going to follow that analogy, then clearly humans are the epitome of that, right? If anything, humans are the example of general purpose. That, however, as a statement, is exactly what cognitive science has spent the last 30 years debunking. If you look at all sorts of cognitive tasks, perceptual tasks, reasoning tasks, people are far from general purpose. I can write letters up on the screen and write out color words and write them in different colored ink. So the word red appears in green ink. And you will suddenly be very good at reading the word red, but unable to name the color green. How is that a general purpose? We can give you tasks, reasoning tasks, like the weights and card sorting task, where we ask you basically to identify a counterfactual. And people are miserable at doing this. Like 5% of first-year undergraduates can do it. Until we turn it into a counterfactual statement about whether or not you're allowed to drink alcohol and what age you are. And then suddenly they're fantastic at it. Even when it's exactly the same problem. We're not general purpose. Now, we would love to be. We like to see ourselves as that. I would like to have general purpose robots. Don't get me wrong. I want those things. I want them to take care of me when I'm old. That's the point where none of you are my students, because none of you jumped up and said you are already, but we want these things. It's just a question of, is the time now? And I don't think the idea that pursuing, well, we need these things in general purpose. We're not. We don't have good examples of very many general purpose things, and almost none at the level of interaction. So that's my answer there.
To add another perspective, I always tell my students, are we building AI? And then, I don't know, is playing chess using AI? And they would all say, no, of course not. Like chess is a very simple problem to solve. When was it? That's probably like 15 years ago, something like that. A little bit more, let's say 20 years ago. When Deep Blue won against Kessler for the first time, that was the end of human intelligence. Like AI took over that day. Well, not so, right? So general purpose is a bit of like what we call general purpose is a bit of a moving target. Maybe what you call general purpose is what our children or potentially our students will call, yeah, that's basic skills that every robot have, like maybe manipulation. Today manipulation, like general purpose manipulation is the kind of thing that Google with RT1, Palm-E is trying to solve, and it's very impressive results. But I'm pretty sure that in a couple of years, that won't be called general purpose anymore. That will be just the basic feature that we can do, that's capabilities of a robot. So I think I fully agree with Skaz. Like, we are not general purpose with our definition of general purpose, but maybe that definition is not. Our robots will still progress and be able to do more things, but that probably won't qualify them as general purpose in the human sense.
Can I reply?
Yeah, absolutely.
So general purpose doesn't mean completely unconstrained. General purpose to me means versatile. And so a general purpose robot that, say, is a domestic robot would be expected to do a large variety of things around the house and obviously handle whatever the user needs them to handle. And in that way, they'd be able to take their knowledge, adapt very quickly to handle new tasks. And it, in many ways, subsumes the idea of personalization, right? In order to learn new tasks as a user would want them to have to be done, you have to first off have a variety of knowledge. You have to be versatile within your domain, and then sure, you can very easily specialize it to it. We wouldn't necessarily expect, say, a domestic robot to go out and, I don't know, cut the grass or something like that, because maybe they have wheels, and wheels don't go too well. Like wheels that would go on, say, a household floor would not work very well on grass or land or hills. And so there could be physical constraints with the robot. That doesn't mean they're just completely unconstrained in terms of what they can do. General purpose means versatile. It means that they're not just specialized to one thing, one user, et cetera, but they can very easily adapt as needed.
Can I also reply?
Yeah, absolutely.
So I think also, I think we have problems with definitions here, like what is general purpose versus what is non-general purpose. And general purpose, I don't think it's a binary thing that we can just pinpoint and say this is general purpose and this isn't. And that's usually the problem with labels like this, with binary labels like this. In philosophy, there is this problem of how do you define someone being bald, having no hair? And if someone has no hair, they're clearly bald. If they have one hair, are they bald? Probably also they're bald. If they have two hairs, are they bald? Probably still bald. But then at some point they have 100 hairs. And then at some point there's this boundary where 100 hairs you are bald, but 101 hairs and you're not bald. And that doesn't seem to make sense either. So there is some kind of spectrum where, it's not that there is one point in time where general purpose begins and specialized purpose stops. But I think we do have a feeling of what general purpose is and what it might look like. And I think even though it's hard to define, we will know when we see it. So they will be versatile. There will be something that you'll probably be able to use in a home. And this is kind of the dream that I think we're all going for. But I don't think we need to necessarily, kind of argue a lot about what general purpose necessarily means and how general purpose humans are. Yes, we are not fully general purpose, but we are further on that spectrum than the robots today.
Yeah, anything to add to that?
I quite agree.
In the end, it will just be like everyone's neutral.
Let me ask one question to the other side here. So if we were going to build something that's general purpose, with whatever boundary definition you would like for that, so inside but not outside, it seems to me that there's right now, let's say, a dozen hard problems that you need to solve to get to that point. Doesn't going after a general purpose system mean that you have to solve all of those dozen problems? That not only do you have to solve one, but you have to solve the hardest of that dozen problems? Isn't this, from just a systems engineering point of view, there is, I think, I agree, there's a good reason to go after those hard problems. But are we just biting off so much more than we can chew right now?
Yeah, I'm happy to start. A lot of this mirrors the ideas of how AI developed in general, right? So a lot of people started on these ideas of general purpose systems, and then it kind of split off into all of these different subcommunities working on individual problems, because it turns out that all those individual problems are really, really, really hard to do, right? And now there's efforts to bring them back together. That doesn't mean, though, that once we are able to bring them back together, all those other efforts were wasted, right? Having those individual studies of all the different hard problems that are needed to solve the big problem is still useful. But once you achieve that big problem, then all of a sudden the payoffs come, right? And so we're talking about what is more impactful. So long term, having the general big system is more impactful, even if the way to get there means we do have to study all those individual problems as we go.
Karol, do you want to edit anything or?
Yeah, maybe one thing I would add, what in my mind makes human-robot interaction a little bit different, is that this technology will fundamentally change. Once we have general-purpose robots, I think it will be very different set of questions we'll be asking and very different research we'll be doing. So I'm worried that if we dive into it right now and we look at what robots can do today and deploy them in some specialized settings and then research how they should interact with humans and how humans react to them, that research will be wiped away as soon as we have more general purpose robots. I think that the modes of interactions, the ways that people react to them will change considerably. So even though I totally agree that it's really, really hard problem and it's even unclear how to approach it, I think it's still more beneficial in the long term to work on that hard problem and to get to that technology, to that capability at first, and then research how it should be deployed and how people should interact with it and how it should be personalized.
I actually have some follow-up, actually. So let's say we do have a general purpose robot at home, but let's assume, for instance, laundry, like, putting the clean laundry into the drawers, but does it exactly the way you don't want it and doesn't change at all. It's completely optimized in terms of engineering, and it puts them away in a certain way that's, takes the least time for the robot, but not the way you can easily find what you want to find when you do it, for instance. So then we start.
Yeah, that's a really good point. I was really keen on going back to the user perspective, because so far we've been mostly discussing the technology perspective. Yes, general purpose robots, that's an interesting research topic.
Yep.
That's quite true. But it's the thing you see when you start deploying robots to the field, to hospitals, to elderly care centers, it's a bit what you're describing, Bahar, is that people actually don't really want the robot to replace or to do things that they were doing before. They are more like, okay, what could be a new role? What can we invent for that robot that would make sense in our context? It's not so much like, well, maybe the laundry, maybe people still want to do that, but it's more about like, we have those social isolation, loneliness issues. Can robots help there without removing any of the human-human interaction we had, but on the contrary, like fostering them? And that's, I don't know if it's really about being general purpose or specific purpose. I don't even know to what extent it's related to personalization, but I think as a field, it's more important to first question and invent and co-create a role for the robots rather than just going as fast as possible for the technology and the technology challenges.
Okay. That was the response. Eric?
Sure. So I think I'd want to start by turning this around on my colleagues here and saying, if you want a robot who can actually personally customize the way that the laundry is put out in the drawers and such, you can find it. How do you possibly do that without starting with a general purpose solution? Starting using that as a prior and then building upon it to the customization. So that's my main argument against it. You kind of need the foundation of that if you even wanted to do the personalization.
But what if you had a laundry robot?
And
It doesn't have to be general, it doesn't have to do the dishes. It's just a laundry robot. And also for, like, if you think about the inclusivity, like for people with disabilities and so on, it might be even better in that case have a personal laundry robot than a general purpose robot that does everything.
I think that can break fairly quickly, right? Like even if you have a laundry robot that, let's say, is personalized to some extent, if something goes wrong, I don't know, like you were supposed to fold a t-shirt and you dropped it on the floor, and you're not general purpose enough to pick it up from the floor, or the shirt is a little wet and you don't know how to deal with that, or it's now on a different surface that you've never seen before and you're specialized to a different surface. I feel like as soon as you would like these robots to expand towards the general purpose robots so that they can be useful even at the task at hand, you kind of start tackling the big questions again. So even though you can narrow it down, we can narrow it down in our heads and think that you can build a robot that does this one thing and you can still deploy it in a home and be useful, I think that assumption will break fairly quickly.
I guess, again, this is a definitional question, but is, picking the object up off the floor part of the laundry robot's purpose, or does that make it general purpose by itself? Even if, as you say, it doesn't do the dishes or something like that. I guess I've been racking my brain trying to come up with something that we would all agree was a general purpose system that was successful in any field, in any domain. Some piece of human engineered equipment that we consider general purpose and successful. And I can't come up with a good example.
Well, you did mention the large language model, Karl, at the beginning of your. That's a really interesting one because, first, I think it's important to acknowledge the fact that this is 4-5 months old. So we have, okay, probably you have insider experience with that for much longer. Let's say that the general impact of those tools is extremely recent. So we have basically no understanding of where it takes us, what we are going to do with that, what we are not going to do with that. But it does, I must agree with you, it does change the perspective we can have on what general purpose means, because those systems are I think we can agree that they are general purpose. They were not, okay, they are just chatbots. So in that sense, there is a single modality, but their content is not tuned to any specific task. They have all the limits that we want, but they are general purpose. It's a really interesting, it's an incredibly exciting, to be fair, change of epistemologic change of about how we are going to think about AI and its impact. But it's just too early to be able to draw any, or it's too early for me to know what to say about it.
Yeah, I mean, just to add to that, I agree. They're very new. They're new to all of us. And they are general purpose. They weren't designed with a specific application in mind. But I do think, even though they're so recent, this is a better analogy to what I think general purpose robots will feel like than inventions from the past. I feel like, the robots we'll have that are out there will need to be able to adapt, will need to be able to have some amount of artificial intelligence that allows them to reason about what is happening in the world, how to adjust their skills and so on. And I think the closest thing that we've seen in the recent history are large language models or are other AI products that have kind of similar properties. And what I think is really interesting is that you could sit down and think of all kinds of different applications and how people interact with large language models before they were developed, right? The concept is fairly obvious. It's a chatbot. I think the amount of things we see right now as to how they're being applied, what kind of fields people consider them applying to, that they can generate code, that they have a lot of knowledge that we didn't even know about, that they could be applied across wide variety of things and they can be readjusted and they have to be aligned with humans and so on. All of these problems and applications, we couldn't think of them up front. And I think it would be very similar with robotic technology.
Anything you want to add?
Yeah, pushing on this just a little bit, looking at the headlines and over the past couple of weeks, months or so about ChatGPT and similar type of technology, and the commentaries on how disruptive it is likely to be across a wide variety of industries. That is impact, right? That is definitely potential for impact. We don't get the same headlines for a specific robot that's being released by a company. Not even if you sum all them together. There's no way. So looking at just, if the question is all about like, how do you have the most impact? And the most impact is clearly pushing toward these general purpose robots.
So I definitely think that, you know, the large language models are a different sort of beast, in that they weren't designed for a specific purpose. But I'm not sure that that actually captures what I think most people think of as general purpose. In that there is that element of problem solving, that element of common sense that I think we do associate with general purpose. You know, if the piece falls on the floor, you've got to pick it up. There's an obvious solution to this. I have no doubt that we can build multi-purpose systems. And I think the large language models are multi-purpose systems. And I think they were not designed for a specific domain. And I think we're still going to be spending the next few years figuring out what they're good at and what they're not. And I think that's really exciting. But I think they're still missing something to call them actually general purpose. Maybe that's just definitional on my part, though.
Maybe one thing I would like to add is I'm really glad that our opponents in this debate now agree that we should be working on multi-purpose systems, not single-purpose systems. I think we're just one step away from general-purpose systems. So give us another half hour, and hopefully we'll get there.
Okay.
I was just going to also discuss or mention the question of around embodiment and because that does bring something that is quite unique to robots. As we know, how is it going to play out with large language model? I have no idea. The first step is what you're trying to do with multimodal models that do not just like text, but also images and things like that. But all the social agency of an interaction with something else is going to be very difficult to embed in the system. I have the intuition that this is a critical part of the equation, but it's exciting research, I would say, at that stage. Yep.
Okay, so what if you were to combine them both? We have a general purpose robot that can actually do personalization, so it can learn from people, like Eric was suggesting, and adapt. Would that be better than personal robots, or would that be still not enough?
It seems to me that one of the things we were discussing is that personalization is part of being general purpose. So to some extent, if you are able to be multi-purpose at least, you will probably also, part of your purpose will be to adjust to the needs and the specific context of the interaction with your users.
So the general purpose is, as far as I understand, it's more like it can adapt to any task and environment, but the user is never in question. User is like, you should use whatever this robot can adapt to, but it's not the user, like the preferences and the needs is not considered. Is that right?
So I think if I understood the question correctly, there was this, the difference between the two statements is we either focus on personalizing single purpose robots or not personalizing general purpose robots. If we can personalize general purpose robots, that's kind of seems like the solution we all want. But I think that brings up another point, which is quite important, which is, I think once we have general purpose systems or multi-purpose systems, the need for personalization is immediate, right? Like it's difficult to imagine a general purpose robot that doesn't personalize to users. Versus if we have a specialized system, we have robots today in factories, and there's no need for personalizing them. They're really good at very specific items, and because they're so special purpose, the kind of added value of personalization isn't that high. But I think as we build general purpose systems in general, and as we see this with large language models, that they have to be personalized to the specific use case or to the specific user, I think in the future as well. Because they are so powerful and they're so general purpose that this need kind of comes out naturally. And I think that's how it's going to happen with robots as well. So even for a field in general, I think it's much more important to focus on general purpose robots, because these are the things where personalization really matters.
So I'm going to disagree with that a little. The difference isn't when you go to general purpose, it's when you introduce humans into the equation. So the factory automation system that's building my car doesn't need to be personalized, because we've controlled that environment to the point where it is as identical each car that rolls down the line as it possibly can be. We don't have anything like that in the home. And it's not because there aren't repetitive tasks we want done in the home, like washing dishes. It's because we're going to put them in a home, and every home is different. Even if they're the exact same layout, they're different because of the people that are in them. So I think as soon as you introduce the human, you introduce the need for that personalization. And I think general purpose systems are going to have it. But I think even specialized systems that work with people are going to need it as well. The other point that I wanted to make is just that there's also sort of a question of what should we as individual researchers do? And the fact of the matter is, while all of us want those big general purpose systems, very few, if anybody, in the community has the resources to go after building that kind of system. If I wanted to, I couldn't build a large language model right now. I've got probably most of the knowledge I need to do it. I've got a fraction of the data, a fraction of the compute power, a fraction of the money it's going to take me to train that system. I think that's going to be even more true when we talk about building physical hardware with real robots. So there's a practical side to this, which is just that if we are going to build a real general purpose robot, there's maybe 2 or 3 research groups in the world that could attempt that. And then what are the rest of us doing?
As a teaser with Tony there, we are putting together a proposal to try to build a model that includes humans.
All right, raise the hand.
First need to get the money though.
Let me reply to 2 things. So you mentioned like the factory and the amount of customization that's needed there. So let's separate customization from personalization, right? So taking the personalization necessarily involves humans, right? But that's another way of saying it's customized to an individual human. All factories are different. They have different processes. So there's a fair amount of configuration and customization that happens whenever you take a general robotic arm and adapt it to the specific task that's being used in the factory. It's just a very different process. For a robot deployed in a home, we would expect that personalization, that customization to happen through natural interaction with humans. And as you said, adding humans in here as a factor is huge, because there's a whole lot of everything from social conventions to language we use to all kinds of things that a system that is able to personalize to us is going to have to contend with. So let me just stop here, and I'll give my colleague a chance to respond if he has anything.
Oh, I fully agree with what was said regarding the practical aspect of it. That saying that there's just a handful of big enough research groups or that have enough resources and data and compute to do this kind of research, and that puts other academic labs, for instance, at disadvantage. I think this is definitely something to think about. This is, I think, something that wasn't obvious from the very beginning when working on AI systems, right? Like, it's just we are kind of entering that branch of AI development that ended up being needed a lot of compute and a lot of data and a lot of resources. It doesn't necessarily mean that this is the only way of doing AI, right? This is just the way that we see right now that is being quite successful. In addition to this, I think if we were to compare how that way of arriving at a general purpose robot compares to something like, let's say, Boston Dynamics way, where there's still a lot of engineering, a lot of ingenuity in that system, but it's not as easily accessible by everybody else, right? So even though you're right that you probably don't have the resources to train a large language model, but there are large language models out there that anyone can use that are really cheap to use, and they will get even cheaper. And I think the same will be true for general purpose AI systems, whether these are multi-model systems or multi-embodiment systems that you can just quickly fine-tune with a little bit of data. And maybe not everybody will be training those big models, but I hope that they will be available fairly easily for academic labs or anybody else to build on top of. So it will be a shared resource that we can all use. And I think that is much more accessible than building a technology that, you know, it's kind of specific to an embodiment, specific to like that requires a lot of engineering, that even if we wanted to, you know, if Boston Dynamics wanted to have it be as accessible, it would be really, really hard.
I'm gonna open the floor for questions. Aditi?
We do have one question from the chat. It doesn't say whether they're online or, so I'll just read it out. The question is, what features do you think are most important in personalization or adaptation to the user? What should the robot change as it interacts with users of different ages, knowledge levels, ableness, etc.?
So I think that clearly has to start on our side, because the answer should do everything for everybody is going to get taken by the other side, right? No, it's a good question, and again, I think the domain is important here. I would love to say that personalization is basically just a whole bunch of different factors, and you can treat them all as variables, and all you got to do is, you know, just pretend that you've got one form of variable or another form of variable, and you can just go from there. But the fact is that when we think about varying over age and varying over social conventions and varying over social norms and language and social structure, things make it very difficult to just standardize. And maybe that's really the thing that's missing. You know, we don't have standards for really describing and declaring what are the ways that things vary as we look to make things change for a specific user. It would be easy to talk about physical form of the robot and whether you like it to be 12 centimeters tall or 14 centimeters tall. It's a lot harder to talk about differences in interaction. Do you like something that is more aggressive with you and challenges you to do things, or do you like something that is more collaborative with you? We don't have good definitions of this from the human side for the interaction. So it's not a surprise that we don't have them for the human to robot side either.
Yeah, I would even want to push that a little bit further. I think making a robot personal to you is not just about changing some surface behaviors, but it's also co-inventing with the robot what the role of that machine will be. And one example of that is with Katie Winkle, one of my former students who is now prof in Sweden, so she's somewhere here. We did put a robot for a couple of months in the hands of it was a gym instructor in that case. And we basically told the gym instructor, way you walk, and the robot will learn. We were using a bit of machine learning, so the robot was learning from this kind of social demonstration. And at the end, after 3 months, we didn't know where it would go. And after 3 months, it was really fun to see the gym coach addressing the robot as his assistant that he just had trained. He was so proud of having trained the robot to do all the stretching at the end of the session. And but yeah, I welcome my new participants or my new customers in that case, and then the robot will do the stretching with the previous one. And that was amazing, but that's a good example of the robot being personalized to the need of that user. But there's no equation for that. There's no variable that we could have thought of beforehand. We were inventing a role, and I think that's at the beginning. If we remove the user, the end user from the equation, we are not doing HRI. We are doing well, not even RI, just R. We need the human to interact, right?
Karol, Eric, you want to add to that?
Sure. So I think that I heard our colleagues say earlier that that personalization is kind of one aspect of being versatile here. And so to me, it's very much that the needs of what should be personalized really depends upon the user as well as the specific task at hand. So for example, you're putting dishes away in isolation, you obviously vary the way you're manipulating objects, right, and configuring them to match the personal preferences of the person in the room. If you have a robot which is helping with, say, physical therapy for recovery after surgery, then there might be very different levels of personalization that are needed to exactly watch the user and see how they're performing exercises and match their individual needs.
Okay. Aditi, want to take the question on Menti?
Sure, yes. We have another question that says, why are these options mutually exclusive? Why can't we have general purpose robots that can also behave differently when talking to different people? I feel like we touched on that a little bit, but.
Yeah, no, the first one, the one on the shared screen.
Oh.
That's the one we just answered, no?
This is the one
Yeah.
that we just answered?
Yeah, that was the first one that I read.
Okay. And the second one, okay. So this is the one that we answered as well. Okay.
Okay, let's see. Don't the research insights that are necessary for developing general purpose robots arise from developments and deployments of specialized robots? Isn't specialization the route to develop general purpose robots?
So I'm happy to start with an answer to this one. I think that yes, that's certainly true in many ways, that we have to work on all these individual problems, but I think it's also really important to keep in mind the end goal of developing versatile general purpose systems and to think about how our individual work would fit into that larger picture. In many ways, we can use it to guide our work. And so instead of focusing on narrow niche problems, we might, by having the lens of how this work would contribute to the development of general purpose robots, adapt our approach just even slightly to make that amenable. Whereas if we didn't have that view, we might miss that completely.
Yeah, maybe to add to that, actually, I don't agree with the premise of the question that the research insights coming from specialized robots are necessary for developing general purpose robots. In fact, we can see a lot of specialized robots today, and we can probably double that or 100x that and have specialized robots for every little thing that you can think of in a factory. And I don't think that will really push us much further in terms of developing general purpose robots. So I don't think, unless we are very, very careful in how we approach specialized solutions so that they are able to generalize eventually and that these insights can carry over, I don't think that happens naturally.
So I tend to agree, actually. I think there are things you don't find when you're building specialized systems that you only uncover when you try to actually put large systems. AGI, I think, supports that. When we start those really ambitious projects to build general purpose things, we often uncover the things that we kind of let go when we were building specialized systems. So I do think there's a role for that. I think just a question of what do you want to spend your time on right now? Because for every one of those AGI systems that uncovers some grand new problem or some brand new technique or solution, there's an awful lot that don't. And I don't know right now whether we're at the point where we're ready for that next big leap.
Okay. Maybe we can take one last question.
Sure. There, okay. I think we kind of already talked about this one as well.
Okay, so
Maybe there's a lot. Okay. General purpose GP sounds great, but the devil is in the details. Even in domains that AI is good at, when we deploy, we discover a million problems. How can we expect a general purpose AI to do well across tasks?
Let's start with Karol.
Yeah, this is a great question. I think we are discovering a million problems, and I think these are the right problems. I think that's why we want to be working on this technology, is to discover these problems and not instead work on problems that we can think of right now that are more tractable, because we can deploy a specialized solution and kind of figure out what the few problems that we'll encounter there are. I think these are just the right problems. This is a very complicated thing that we are dreaming of, that we are planning to deploy and to have in people's lives. Having an intelligent robot that can do a lot of different things at the home is a really difficult problem, and it's very underdefined as well. So even once we have something that we can agree is general purpose robot, I think there will be a lot more things that will come with it that we would need to grapple with, as we see in the large language models world. But I do think these are important problems, and this is the right research to be working on.
Eric, you want to add to that?
Yeah, so I view the idea of a general purpose system as kind of the starting point for further specialization. So if I have a general purpose robot in my house, it learns the tasks that I needed to learn in the ways that I needed to learn it, and then it starts to become specialized to handle those tasks. That doesn't remove its capability of taking that robot into someone else's home and have it again re-customized to whatever task that person needs. It forms essentially a prior for all that specialization. And even if you look at a lot of these very specialized applications where you have an application that you're deploying a robot for, it's finely tuned on a whole bunch of data, that's still being built upon for largely general purpose learning algorithms and other techniques, which are general purpose, which could be applied to a variety of different problems. Even if the output of that's actually deployed is specialized, the foundations of how that output came from are all more general algorithms. So I guess one of my main arguments is take that general purpose versatile learning style approach and bake it into the robot itself so that it itself can go from a general purpose or versatile robot into one that's specialized to the needs of the tasks or the domains where it's deployed.
I hope we build general purpose systems. I hope we are successful with it. But for now, I think I'm going to go back to the statement that I started with, which is this is much more about the human side than the technology side. All things being equal, I'd love to see the more general technology be developed. But the consideration that we danced around but haven't actually talked about today is what impact that technology has. Are those things going to put hundreds of thousands or millions of people out of work? Probably not. Are they going to change our economy? Yeah, probably. You put a real general purpose system out there, that's fundamental change. I would like to spend some time with the special purpose systems so that we can actually study the impact of these, actually understand and make predictions about what kinds of changes they're going to make, and decide whether we want to put limitations on or not. So that's where I fall right now.
Yes, me too. That was the fact that I think we should always ask the end users what they need and what they want. And if the robot is helpful, of course, you cannot imagine what a robot can do for you without first having some experience using it or seeing it deployed. But that needs to be done, and done in an open, honest mind, like, oh, this is what technology can do. Maybe it can be a little bit multi-purpose, can do several things, tell us what is actually useful, and what will make us better humans or more humans or having more time to spend between humans and not just replace us.
Any last points on that, Eric and Karol?
So I think going back to what I said before is that I think, to me, the main role of a versatile robot is to serve as the foundation for personalization for specific tasks.
You think so? Like, sorry, go for it.
Oh yeah, maybe just a response to Brian's comment, which I think makes a lot of sense. I think that's kind of how you would plan that, so that you deploy specialized systems first, you learn from them, you learn how they should be interacting with humans, how to maybe guardrail them, and so on. And that informs your decisions on general purpose systems. I think where the rubber meets the road is these general purpose systems are qualitatively different. So even if we did a lot of studies on, how let's say code autocompletion helps people with coding and what kind of impact on coders it will have and so on, we'll draw very different conclusions with the systems that we had before that were specialized for this, that were helping a little bit here and there, compared to what large language models can do right now and how they can generate code right now. So I'm worried about the conclusions about the fact that the conclusions will not transfer between the specialized solution and the general purpose solution.
Interesting, perfect. Okay, so you heard from our experts on both personalization and generalization aspects. Now I ask you again. Sense. What? Do you think you agree that it's more impactful to focus on building robots that personalize effectively to users in a constricted task or application than to build more general purpose robots? Everyone's neutral now. See, or first, oh wow, interesting. Wow, yeah. Uh-huh. It's not a fight. It is a fight. Oh yeah. It's winning slowly.
Someone will disagree for everybody to be happy.
Yeah.
Yeah.
But I think like we changed people's opinions, and I think that's the most important part of the debate. It's like there are people who were agreeing before now are disagreeing, or that the neutral is actually less, so they actually have an opinion now. So that's the most important part. So let's try to not go like who wins, who lose. Everyone's a winner. We all work on robots. Okay, I guess everyone voted. Yeah, I mean, this is a workshop on lifelong learning and personalization. Of course, it's gonna be more agrees on personalization, but still, I'm happy to see the change. And I would like to thank my debaters for coming here and for being there, for attending. And for me, it was a great pleasure to talk with you, to discuss with you all this, and to like have your opinion inside as well. Hope you enjoyed it.
Thank you.
Thank you for having us.
Thank you for having us. This was a lot of fun.
Thank you. Perfect. Now we're going to go into the discussion for the workshop. Hey, Eric, bye, Karol. Thank you so much for coming. And I'm gonna give it to Hatice for this short. Yeah. Thanks.
So we just wanted to gather some opinions because since we started organizing this workshop, it has always been only virtual. Actually, this is the first one that's sort of physical and hybrid. So it's good to see some faces and maybe we can gather some opinions about the future of the workshop. That's the main goal, but we'll keep it short, I promise. So we'll already prepared some questions. So I will just ask actually also online as well. You know, what is your biggest takeaway today? Anything you would like to share with us so we can actually close in mind also for future as we tailor, because this was the first debate, in fact. Previously we didn't have debates, so it was mostly having invited talks, and then I think we had discussion as well, panel, the prototypical way was invited talks panel. This year I suggested debate, and I think it went really well. So we're trying to vary a little bit, so it's good to hear some feedback and your comments. So that's the main idea. So what is your biggest takeaway today? You think, I mean, it doesn't have to be actually about personalization, but it could be also just, yes.
Yeah,
Sorry, you'll have to come.
Oh,
okay. It's the pain of the, well, or pleasure of being hybrid. Yeah. So you have to talk there and this one as well.
So I think I speak for many people that I find the debate really interesting. You know, I picked this work not because I work in this area specifically, but of course I work in robot interaction in general. So this is interesting, but isn't this like particular aspect of personalization or lifelong learning? But I think the question of the debate is very interesting, very relevant. To the workshop, but also I think actually to the community in general. I feel really bad for people who couldn't be here today and hear this really insightful debate. And I think that is the aspect that I like the most about today's experience. In addition to the paper presentations and also the main talk by the two speakers. And I would have a suggestion is that you guys do the same debate, same topic in a year's time. And I think at that time, when the technology has changed, I'd imagine a lot. Perhaps even with the same people, and then I'd be very interested to come again and hear you know how their opinions have changed and evolved, or perhaps the same, and how does that reflect the technological change that has happened in the past year from 2023 to 2024.
Thank you for sharing. In fact, we were going to break out a session where we wanted to discuss a little bit about these large language models, and indeed they were covered by the debaters as well. How, for instance, ChatGPT type of models will affect the community, you know, social robotics, human-robot interaction, and so on. So maybe in a year's time we'll start. I already started seeing some papers on archive. So yes, this might change, but probably not the same debate. The same people might be competitive. But yes, I understand. You know, things will evolve differently in various directions. Yes, just feel free to come. Keeping it quite informal.
Oh, okay, hello. This is my first time to physical attend the human-robot interaction. I'm a community student, and then I'm really new this area, but I'm interested to keep this workshop. I really like this debate session, because I can. So because a lot of senior professors to show their ideas, and then when I see the question the point of was as a student, I think about how if I debate, how can I answer this question, and then compare their professors, and can improve my mind, open my mind. I think it's really good. The suggestion I really want, maybe in the future, so in the physical, the audience, we can separate the two groups. So I think maybe we can, we can invite each group of one or two audience to show their ideas, and this support our team, so more engaged. So I think
more heated. It's a big group, so it's difficult to engage. That's why we wanted to do the mentee.
So I think some audience want to share their ideas. That is all. Thanks. Yeah.
So my understanding from this is to engage the audience more, probably. Yeah, that's the takeaway I'm hearing. Any would like to share? If not, we can just. Are there any online? Yeah, there's. Okay, let me just have a look. Do please ask the speaker to talk. Okay, that was sorry. Let me filter before I read.
Yeah, just the ones on the screen.
Okay. So should I read all of them? Yeah, or we just pick
we
some
will
because
see,
it might take some time. I think the debate was amazing. So that's sort of, in a way, echoing what we already heard. Personalization is complex, difficult, and important. I think that we all know that, and that's why they're keeping on organizing these workshops, hoping to get there. Presentation, seeing cool new technologies and methods, debate, general purpose and specialized drive each other and each give unique insights and developments. I think we have achieved the goal. That's what I'm gathering from this. Okay, so moving on to the next one. Yeah, okay. Okay, what specific things we can do to improve? So not so much what you liked and what you can take away, but maybe what you didn't like and how we can improve future editions and, you know, further in terms of incorporating perhaps different aspects, because as Bahar said, we also have different organizers, not because we were changing, but people move on, and we also, you know, change directions slightly. As I said, we incorporated debate this year. But if there are certain things that you, would prefer to change, to improve for the workshop in terms of content, or perhaps speakers you would like to see or topics you would like to hear more about related to the generic aspect of LEAP-HRI. Obviously, we want to stay true to our workshop and our purpose. Yes, please come. If you can get close, because we always complain.
Hello, and thank you again. Yeah, it was wonderful. This is the home of fur hats, so I thought it would have been great to have a fur hat robot in the debate for next year.
ChatGPT.
Yeah, it's possible, right?
Yeah, that would go wrong so many ways. Yeah.
Go for it. You know, it's a robot conference without robots. Yeah, bring in the robot.
Should we do the Turing test again? Okay, yeah, something to consider. Yeah. Thank you. Anything else aside from bringing robots in?
I think we're just so good. Nothing to.
Well, I think it's the end of the day as well.
Yeah.
So that's why we're asking at the end, so you can't say much about the aspects you didn't like. But anyway, I mean, if you can't think of right now, if you have any suggestions, please feel free to email us. It's really important to get feedback for us. Oh, there are some. Okay. Oh, that's good. Yeah, okay. I know the hybrid, I'm also learning, so I completely agree. I think this is probably part of the evolution now. We are at a stage as humanity living hybrid lives, not just, you know, during the pandemic, it was more virtual lives, and before that was more physical, and now we are at a stage where the life, at least conference life, is more hybrid. So I think it's for all of us sort of developing the behavior of how to interact in a hybrid sort of conference setting. And I also agree, I think we're all a little bit struggling. I was giving, in between, I was giving a talk in another room. So I was told to look specifically certain way so that my voice can go, you know, online and spontaneous to the audience. So I think it's just, I would say evolution. Online speakers present via video instead of live, maybe a section that would be more interactive. So these interactive aspects keep coming perhaps.
I would suggest, like, I would go with live, because I understand that there's like internet connection problems, but like it changes so like, it change. Okay, right. I'll do it. Okay, you can. Oh, I'm tall. Okay, so I would actually prefer doing it live, and I always like really like step my foot on this one, because like when it's recorded, no one will listen to it as you would a live talk, because I mean I know, yeah, we're internet, we have terrible issues, but it's just not the same. Like with the live, the speaker can see you. You can see the speaker. It's more like a mutual interaction. Recorded, it's not the same. So I'm sorry, I'll skip that one. But I mean, great suggestion. But yeah, go.
Okay, so I think this interaction aspect, people want to be more involved. That's what I understand. Yes, because this year we didn't have breakout sessions. Previous editions, we actually had the breakout sessions where there was more interaction. Yeah. Discuss some definitions. Yeah, I think that's probably, maybe we should provide generic definitions before if you're going for a debate and so on. I don't know if that relates to that.
I think like even with the experts, like, I mean, they're all experts in personalization and generalization, right? They couldn't define, like, there is no one thing that we can just like all agree on the single definition. Like, what is a social robot? What is a robot? We don't even agree on that. So I think like we should definitely discuss more definition. That could be like a session or something. Like we could try to all together, like bring in minds and try to figure out something and just make the community know, so that it's more like easier to do a debate on top of that.
I think we have if you want to just get closer.
Okay.
So from the audience, we have more suggestions.
Yes, first of all, thank you for the great workshop. And my suggestions is about the debate. Maybe next time we could introduce some rules, like in the professional debates, to have an opening case where would be a resolution with a definition, so we could make it more specific, more exact, and we will have ranges. So opening case, closed case, resolutions, like just in the real debates on a professional level. So thank you.
Okay. Yes, this is our first debate experience. So we need to perfect it as well. Thank you. Looking around, I think no more. One more. One more. Oh, okay, yeah. Okay, to include speakers from underrepresented communities. I think, I mean, if there's specific suggestion for certain please also feel free to email us if you don't want to share publicly. Not many people work on lifelong learning and or personalization. So as we continue having the workshop year after year, you know, our choices or options become limited, not because we don't want to have people from underrepresented communities, but even trying to balance female, male, even at that level, we start struggling. So if you know people who work on these areas and we are not aware of, so please just send us an email. We would love to include them. So that very, very open to include them as organizers as well, or as speakers. We'll definitely consider that. Okay. Oh, okay, that's the, would you attend LEAP-HRI next year? Give us an applause. If yes.
Yeah. I'll just...
And if not, you can start leaving already. No, thank you so much. Thank you so much for being here, even till the last minute. We really enjoyed it, and it seems you enjoyed it as well. And Bahar, thank you so much, because she's been the main driving force of this now for 3 years. So a big applause for Bahar.
And thank you to my co-organizers, Hatice here, Aditi and Mariacarla over there. They've been extremely, extremely helpful. I mean, like, we don't even have to have meetings. Like, it's just emails. We can just do everything through email. Completely efficient people. Thank you all so much.
I also want to thank you, especially Bahar, for having coordinating this workshop. Really, very, very good work.
Thank you. Yeah, it's the woman in robotics, people.
Yeah, exactly. Yours power.
Thank you, and thank you all for coming. Thank you very much. I hope you have a great HRI and enjoy the amazing Stockholm. Hey.
Thank you.
Bye, everyone.
Thank you for your virtual attendees as well.
See you.
Hey, bye.
Bye-bye.
Bye.
Bye.